Entire ecosystems have shifted under the shadow of a predator that refuses to specialize. Across the world's tropical and subtropical oceans, fisheries collapse, coral reefs transform, and migratory routes bend in response to a hunter whose appetite rewrites ecological rules. The tiger shark does not merely occupy the sea, it alters its structure, redistributing life through relentless consumption. Where it patrols, the balance between herbivores and algae, scavengers and carcasses, stability and chaos becomes fluid. Its influence extends beyond the surface of the water, shaping coastal economies, altering the fate of endangered species, and determining the resilience of entire marine systems. This is not the story of a precise hunter executing perfect strikes, but of a biological anomaly that thrives on unpredictability, a predator whose refusal to discriminate has made it one of the ocean's most consequential forces. The tiger shark's biological design explains this unsettling power. Its broad, blunt snout houses an array of sensory systems capable of detecting electrical impulses, minute vibrations, and chemical traces diluted across vast distances. Rows of serrated, saw-like teeth, curved and deeply notched, allow it to slice through bone, shell, and cartilage with equal efficiency. Unlike more specialized sharks whose teeth are adapted for gripping slippery fish or crushing armored prey, the tiger shark's dentition is a universal tool, engineered to dismantle almost any organism it encounters. This anatomical versatility is supported by a remarkably elastic stomach, capable of expanding to accommodate large or irregular objects, while a highly acidic digestive system dissolves materials that would defeat most predators. Evolution has not refined this shark into a master of precision. Instead, it has shaped a creature optimized for uncertainty, capable of surviving in fluctuating environments where predictable food sources cannot be relied upon. When scarcity emerges, this biological flexibility becomes an extreme survival strategy. Hunger strips away selectivity, transforming the tiger shark from a deliberate predator into an opportunist of astonishing breadth. Sea turtles, seabirds, rays, crustaceans, carrion, and even inanimate debris fall within its range of consumption. This indiscriminate feeding behavior is not reckless chaos, but a calculated response to environmental instability, allowing the shark to persist in ecosystems where seasonal migrations, climatic shifts, or human exploitation disrupt traditional food chains. In periods of scarcity, precision becomes a liability, and adaptability becomes the currency of survival. The tiger shark embodies this principle, turning uncertainty into advantage by exploiting whatever the ocean provides. The consequences of this behavior ripple outward in profound ecological cascades. In regions where tiger sharks patrol seagrass meadows, their presence reshapes the grazing patterns of herbivores such as dugongs and green sea turtles. These animals, aware of the shark's unpredictable appetite, abandon exposed feeding grounds, allowing seagrass to regenerate and stabilize sediment along coastlines. This process protects shorelines from erosion, preserves carbon stores trapped within marine vegetation, and supports biodiversity that depends on healthy seagrass ecosystems. Remove the tiger shark, and herbivores return unchecked, stripping meadows bare and triggering a chain reaction that destabilizes coastal habitats. Thus, the predator's indiscriminate feeding strategy exerts a paradoxical form of control, maintaining ecological equilibrium through fear and unpredictability. The cascade extends beyond seagrass into coral reef systems. Tiger sharks prey upon mesopredators such as rays, which themselves consume shellfish and crustaceans, that maintain reef health. When tiger sharks decline, ray populations surge, leading to the depletion of benthic organisms that stabilize reef structures. The result is a subtle yet profound shift in ecosystem composition, where once resilient coral habitats become vulnerable to collapse. Through this intricate network of trophic interactions, the tiger shark's opportunistic feeding habits influence not only individual prey species, but the architecture of entire marine landscapes. Each indiscriminate meal reverberates through the food web, reinforcing the predator's role as an ecological regulator. Yet the tiger shark's hunger carries inherent risks. Unlike specialized hunters that target predictable prey, this species ventures into dietary territory fraught with danger. Hard-shelled animals can cause internal injury, venomous species pose toxic threats, and unfamiliar objects may prove indigestible. The digestive system's formidable acidity and muscular strength mitigate many of these dangers, but the gamble remains ever present. This willingness to consume the unfamiliar reveals a profound evolutionary trade-off. Survival through flexibility comes at the cost of increased exposure to harm. In an environment where starvation is a constant threat, the tiger shark accepts this risk, turning the ocean into a perpetual wager between nourishment and peril. Human civilization intersects with this anomaly in unexpected ways. Coastal fisheries, tourism industries, and conservation initiatives all feel the influence of tiger sharks. By regulating populations of herbivores and mesopredators, these sharks contribute to the stability of habitats that support commercially valuable species. Healthy seagrass beds and coral reefs nurture juvenile fish, sustain biodiversity, and protect coastlines from storm surges. The presence of tiger sharks, therefore, indirectly supports economies dependent on marine resources and shoreline protection. Conversely, their decline can trigger ecological imbalances that undermine fisheries, accelerate habitat degradation, and erode the natural defenses of coastal communities against rising seas. The relationship between tiger sharks and human activity reveals another dimension of their impact: their role as scavengers in the marine environment. By consuming carrion, including the remains of whales and other large animals, they accelerate nutrient recycling within the ocean. These feeding events redistribute organic matter across ecosystems, fueling microbial communities and supporting complex food webs that extend from the depths to the surface. In this way, the tiger shark functions not only as a predator, but also as a biological recycler, ensuring that energy flows efficiently through the marine system. Such processes, though invisible to most observers, sustain the productivity of the oceans upon which humanity depends. An unexpected twist emerges from this narrative of dominance and resilience. Despite their formidable adaptability, tiger sharks are vulnerable to human exploitation and environmental change. Overfishing, habitat degradation, and pollution threaten their populations, disrupting the very ecological processes they help sustain. Ironically, the same indiscriminate appetite that allows tiger sharks to survive in unstable environments also exposes them to danger, as they ingest marine debris and toxins introduced by human activity. Plastic fragments, fishing gear, and contaminated prey accumulate within their bodies, illustrating the perilous intersection between biological adaptability and anthropogenic influence. The predator that thrives on unpredictability becomes a victim of a rapidly changing ocean shaped by human hands. This vulnerability reframes the tiger shark's role in the marine world. Rather than an invulnerable apex predator, it emerges as a fragile keystone species whose decline could destabilize ecosystems on a global scale. The disappearance of tiger sharks would reverberate through seagrass meadows, coral reefs, and coastal economies, triggering cascading effects that extend far beyond the boundaries of their habitat. Such a loss would not simply remove a predator from the ocean, it would dismantle a system of ecological checks and balances forged over millions of years. The tiger shark's anomaly lies not only in its indiscriminate feeding, but in its capacity to shape the destiny of entire ecosystems through the simple act of survival. As ocean temperatures rise and human pressures intensify, the stakes of this anomaly grow ever higher. Changing climatic conditions alter prey distributions, forcing tiger sharks to expand their ranges and encounter unfamiliar environments. In these shifting waters, their opportunistic feeding strategy becomes both a lifeline and a liability, enabling adaptation while increasing exposure to new risks. The interplay between hunger, adaptability, and environmental change underscores the precarious balance upon which marine ecosystems depend. Each meal consumed by a tiger shark represents a decision shaped by evolutionary necessity, a gamble that determines not only its survival, but the stability of the oceanic world. The final image emerges in the dim light beneath a restless sea. A solitary tiger shark glides through shifting currents, its striped flanks dissolving into shadow, its senses attuned to the faintest trace of life. Hunger guides its path, stripping away preference and precision, transforming the boundless ocean into a landscape of opportunity and risk. In its wake, ecosystems adjust, coastlines endure, and human livelihoods persist, bound to the silent decisions of a predator that refuses to choose. The tiger shark is not merely a hunter, it is an agent of transformation, a living anomaly that reminds us the ocean does not simply exist. It acts. It reshapes the world. Entire reef systems have shifted under the silent influence of a creature that rarely leaves a trace, yet whose decisions ripple outward through food webs, fisheries, and coastal stability. In the shadowed crevices of coral labyrinths and volcanic seafloors, octopuses regulate populations of crustaceans, mollusks, and small fish, shaping the architecture of benthic ecosystems across the world's oceans. When their numbers fluctuate, shellfish beds surge or collapse, reef communities reorganize, and the balance between predator and prey tilts with cascading consequences. These changes reverberate into human economies dependent on fisheries and coastal biodiversity. The octopus does not dominate through brute force or territorial conquest. Instead, it alters ecosystems through intelligence, precision, and adaptability. Yet beneath this mastery lies an anomaly shaped by desperation. For when hunger intensifies, caution erodes, and the ocean's most secretive hunter is compelled to gamble with its own survival. The biological machinery behind this transformation is unlike that of any other marine predator. The octopus possesses a decentralized nervous system in which the majority of its neurons reside within its arms, granting each limb a degree of autonomy and sensory awareness. This distributed intelligence allows the animal to manipulate objects, solve complex problems, and coordinate fluid movements with extraordinary precision. Its soft, boneless body can compress through apertures scarcely wider than its eyes, enabling access to refuges inaccessible to most predators. Chromatophores, iridophores, and leucophores, embedded within its skin, function as dynamic optical organs, altering color, texture, and reflectivity in fractions of a second. These cellular mechanisms enable instantaneous camouflage, transforming the octopus into a living mirage capable of vanishing against rock, sand, or coral. Normally, such adaptations ensure survival through concealment and ambush, allowing the octopus to hunt cautiously from within the safety of its den. When prey is abundant, this strategy preserves energy while minimizing exposure to danger. The octopus remains concealed within crevices, extending an exploratory arm into the surrounding environment to detect chemical signals and tactile cues. Its suckers, each lined with thousands of chemoreceptors, taste the water and identify potential prey with remarkable sensitivity. A swift, calculated strike follows, injecting venom through a chitinous beak to immobilize crabs, mollusks, or fish. The process is efficient and precise, reflecting a life governed by calculated risk. Yet this equilibrium is fragile, dependent upon stable prey populations and environmental conditions that support predictable feeding opportunities. Scarcity disrupts this balance, forcing a radical shift in behavior that reveals the octopus's vulnerability beneath its brilliance. As preferred prey declines due to seasonal fluctuations, environmental change, or human exploitation, hunger begins to override caution. The octopus abandons the safety of its den, venturing into open terrain where concealment offers limited protection. It hunts during daylight, crosses exposed seabeds, and confronts unfamiliar prey with increasing urgency. This escalation is not born of recklessness, but of necessity, a biological response to metabolic demands that cannot be deferred. The octopus's intelligence remains intact, yet the circumstances of starvation compel it into perilous situations where even the most sophisticated camouflage cannot guarantee survival. These risk-driven movements initiate cascading effects throughout marine ecosystems. As octopuses expand their hunting range, they exert pressure on previously unexploited prey populations, altering the distribution of crustaceans and mollusks across reef systems. Shellfish beds that once flourished in protected niches experience intensified predation, while small fish and invertebrates encounter a predator in habitats where they had evolved with relative security. Such shifts reverberate through food webs, influencing species composition and ecological stability. In regions where octopus populations surge during periods of prey scarcity, fisheries targeting shellfish and crustaceans experience sudden declines, illustrating the profound influence of this solitary predator on commercial resources. The escalation of risk also transforms the octopus from a hidden regulator into an exposed participant in the broader predator-prey dynamic. By venturing into open waters, it becomes increasingly vulnerable to sharks, moray eels, groupers, and marine mammals. Encounters with these predators rise sharply as hunger drives octopuses beyond the protective confines of their dens. The resulting mortality not only reduces local populations, but also redistributes predatory pressure across ecosystems, creating feedback loops that reshape community structure. Each foraging decision made under the influence of starvation carries consequences that ripple outward, influencing biodiversity, resource availability, and the delicate equilibrium of marine habitats. A new layer of complexity emerges as these ecological cascades intersect with climate systems and ocean chemistry. Octopuses, as voracious consumers of crustaceans and mollusks, indirectly influence populations of grazing organisms that regulate algal growth on coral reefs. By controlling these populations, they contribute to the maintenance of reef health, preserving habitats that support immense biodiversity and stabilize coastal ecosystems. When hunger drives octopuses into new territories, their altered feeding patterns can disrupt these regulatory functions, intensifying algal overgrowth or depleting key invertebrate species. Such changes affect the resilience of coral reefs, ecosystems that serve as natural barriers against storm surges and as reservoirs of marine life essential to global fisheries. Human civilization is intricately entwined with these dynamics. Octopus fisheries represent significant economic resources in coastal regions across the globe, sustaining livelihoods and contributing to international markets. Fluctuations in octopus populations, driven by environmental change or shifts in prey availability, can dramatically influence supply chains and local economies. Moreover, the species' role in regulating shellfish populations intersects with aquaculture and commercial harvesting, illustrating the complex interplay between ecological balance and human enterprise. As climate change alters ocean temperatures and acidity, prey distributions shift, compelling octopuses to adapt their foraging strategies and, in turn, reshaping the availability of marine resources upon which human communities depend. Yet the most profound impact of risk escalation lies in the biological paradox it reveals. Despite their intelligence, adaptability, and remarkable camouflage, octopuses are fundamentally fragile. Their soft bodies offer little protection against predators, and their lifespans are brief, often measured in only a few years. Starvation forces them into exposed environments where the margin between survival and death narrows dramatically. This vulnerability is compounded by environmental stressors such as warming oceans, habitat degradation, and pollution, which disrupt prey availability and intensify the pressures that drive risk-taking behavior. The octopus, a symbol of ingenuity and adaptability, emerges as a creature perpetually negotiating the boundaries of survival. An unexpected twist deepens this narrative of resilience and peril. In certain regions, octopus populations have expanded in response to overfishing of their predators, a phenomenon that transforms them from vulnerable prey into dominant opportunists. This surge has reshaped marine ecosystems, altering species composition and influencing fisheries in unpredictable ways. Yet this apparent success conceals an inherent instability, for the same environmental forces that enable octopus proliferation can swiftly reverse their fortunes. The rise of this enigmatic predator thus embodies both adaptability and fragility, revealing the delicate balance upon which marine ecosystems depend. As hunger compels octopuses to abandon caution, the consequences extend beyond individual survival into the realm of global ecological systems. Their risk-driven foraging alters food webs, influences fisheries, and reshapes the resilience of coral reefs and coastal habitats. Each decision to leave a sheltered den reflects a negotiation between metabolic necessity and existential danger, a silent calculation performed beneath the waves. The mistake is not one of incompetence or misjudgment, but of circumstance, a testament to the unforgiving realities of life in the ocean's depths. The final image unfolds in the dim blue light of a reef at dawn. An octopus glides across open sand, its skin shifting through a spectrum of colors as it abandons the sanctuary of its den in search of sustenance. Around it, predators patrol the water column, their silhouettes etched against the rising sun. Every movement carries risk, every foraging attempt a gamble dictated by hunger and necessity. Beneath the surface, ecosystems adjust, prey populations fluctuate, and human livelihoods remain tethered to the fragile equilibrium maintained by this solitary hunter. In its silent ascent from shadow to exposure, the anomaly becomes unmistakable. The ocean does not merely exist. It acts. It reshapes the world. Across the vast drainage of the Amazon basin, entire ecological systems shift when water levels fall and food becomes scarce, triggering a phenomenon capable of transforming calm rivers into theaters of sudden explosive predation. The piranha, often misunderstood as a perpetual menace, reveals its true planetary significance not through constant aggression, but through episodic surges of collective feeding that reshape freshwater ecosystems. During seasonal droughts, when rivers contract into shrinking pools and competition intensifies, these fish unleash feeding frenzies that redistribute nutrients, regulate populations, and accelerate decomposition across the largest tropical watershed on Earth. Such events ripple outward through the Amazon's intricate hydrological networks, influencing fisheries, biodiversity, and carbon cycling in ways that extend far beyond the moment of attack. The piranha's anomaly lies not in relentless violence, but in its capacity to transform environmental stress into ecological upheaval, revealing how hunger can catalyze forces that reshape both river and rainforest. The biological mechanisms underlying this transformation are rooted in anatomy and sensory precision. Piranhas possess laterally compressed bodies engineered for rapid bursts of speed, allowing them to pivot and strike with remarkable efficiency in confined waters. Their jaws, powered by robust adductor muscles, close with extraordinary force, while interlocking triangular teeth form a continuous cutting edge capable of shearing flesh and bone in a single motion. This dentition is not designed for tearing, but for slicing, ensuring that each bite removes a precise fragment of tissue with minimal effort. Complementing this formidable hardware is an acute sensory system attuned to vibration, chemical signals, and visual cues. The lateral line detects minute disturbances in the water, while olfactory receptors identify traces of blood or organic decay. Under normal conditions, these adaptations support opportunistic feeding on fish, insects, seeds, and carrion. Aggression remains restrained, governed by the balance between risk and reward that defines life in the Amazon's complex waterways. When environmental stress disrupts this equilibrium, the behavioral landscape shifts dramatically. As rivers recede during seasonal droughts, vast floodplains contract into isolated lagoons, concentrating fish and depleting available resources. In these confined environments, hunger intensifies competition, and piranhas respond with heightened vigilance and agitation. A single wounded organism or fragment of carrion can ignite a feeding response that spreads through the shoal with astonishing speed. Each bite releases chemical cues into the water, amplifying the stimulus and drawing additional individuals into the frenzy. This escalation is not chaotic, but driven by biological feedback loops, where sensory detection and social facilitation synchronize the actions of the group. The result is a rapid chain reaction, transforming individual hunger into collective predation that unfolds with startling efficiency. The ecological cascade triggered by such events extends far beyond the immediate act of feeding. By rapidly consuming weakened or dying animals, piranhas accelerate the decomposition process, redistributing nutrients throughout the aquatic ecosystem. This rapid nutrient recycling fuels microbial activity, supports plankton blooms, and sustains the productivity of the Amazon's vast food web. The aftermath of a feeding frenzy enriches sediments and water columns alike, ensuring that energy flows efficiently from prey to predator and onward through the ecosystem. In this way, the piranha functions as both predator and recycler, shaping the chemical and biological dynamics of one of the most biodiverse regions on Earth. As these nutrient pulses disperse through interconnected waterways, their influence reaches the surrounding rainforest itself. Seasonal floods transport enriched sediments onto floodplains, nourishing vegetation that forms the foundation of terrestrial food webs. The productivity of these floodplain forests, sustained in part by nutrient inputs derived from aquatic predation, supports an astonishing array of species, from insects and birds to mammals and reptiles. Thus, the feeding frenzy of a piranha shoal contributes indirectly to the vitality of the Amazonian rainforest, illustrating how localized events within a shrinking pool can reverberate across an entire biome. Each surge of collective feeding becomes a catalyst for ecological renewal, reinforcing the intricate interdependence between river and forest. Human civilization intersects with this anomaly in profound and unexpected ways. The Amazon basin supports millions of people who depend upon its fisheries for sustenance and economic stability. Piranhas, both as predators and prey, play a pivotal role in regulating fish populations and maintaining the health of aquatic ecosystems upon which local communities rely. Their consumption of diseased or weakened organisms reduces the spread of pathogens, safeguarding the productivity of fisheries and contributing to food security. In addition, their presence influences fishing practices, cultural traditions, and local economies, shaping the relationship between human societies and the dynamic waters of the Amazon. The consequences of feeding frenzy conditions extend into global markets and environmental resilience. The nutrient cycling driven by piranha predation contributes to the productivity of fisheries that supply regional and international demand. Moreover, the ecological stability of the Amazon basin, sustained by the interplay of aquatic and terrestrial systems, plays a critical role in regulating the Earth's climate. Floodplain forests, supported by nutrient-rich sediments, store vast quantities of carbon, moderating atmospheric carbon dioxide levels and influencing global climate patterns. In this context, the episodic feeding behavior of a shoal of piranhas becomes part of a broader system that links freshwater ecosystems to planetary stability. A surprising dimension of this narrative emerges from the true nature of piranha aggression. Contrary to sensationalized portrayals, piranhas are not perpetually violent predators, but cautious omnivores whose behavior is governed by environmental conditions. Feeding frenzies arise only when hunger coincides with ecological stress, such as low water levels or limited food availability. Under stable conditions, these fish coexist peacefully within diverse communities, feeding on fruits, seeds, and small invertebrates. This behavioral plasticity reveals a species finely attuned to the rhythms of its environment, capable of shifting from opportunistic foraging to collective predation when survival demands it. The frenzy, therefore, is not a manifestation of inherent ferocity, but a biological response to scarcity and competition. This adaptability introduces a paradox that reframes the piranha's role within the Amazon. Despite their formidable reputation, piranhas are themselves vulnerable to environmental change and human exploitation. Overfishing, habitat degradation, and alterations in hydrological cycles threaten their populations and disrupt the ecological processes they sustain. Climate change intensifies droughts and modifies flood patterns, altering the timing and frequency of feeding frenzies and reshaping the delicate balance between predator and prey. The very environmental pressures that trigger collective predation also expose piranhas to uncertainty, underscoring the fragility of a species often perceived as invincible. As environmental stress intensifies across the Amazon basin, the chain reactions initiated by piranha feeding frenzies become increasingly significant. Reduced water levels concentrate fish populations, heightening competition and amplifying the likelihood of rapid, coordinated predation. Each feeding event releases a pulse of energy and nutrients into the ecosystem, reinforcing the productivity of aquatic and terrestrial habitats alike. These pulses sustain biodiversity, regulate populations, and maintain the resilience of one of the planet's most complex ecosystems. In this way, the piranha emerges not as a symbol of chaos, but as a catalyst of balance, its episodic aggression woven into the ecological fabric of the Amazon. The broader implications of this phenomenon extend beyond the rainforest to the global stage. The Amazon basin functions as a vital component of the Earth's hydrological and climatic systems, influencing weather patterns, carbon storage, and biodiversity on a planetary scale. The health of its waterways, sustained in part by the nutrient cycling driven by piranha predation, underpins the stability of ecosystems that support both wildlife and human societies. Each feeding frenzy, triggered by hunger and environmental stress, becomes a microcosm of ecological interdependence, demonstrating how localized biological processes contribute to global environmental equilibrium. In the final image, the river lies silent beneath a copper sky as the dry season tightens its grip upon the land. Shallow waters shimmer with suspended silt, and shadows gather beneath the surface as a shoal of piranhas circles in restless anticipation. A single disturbance breaks the stillness, releasing a ripple that spreads through the water like a pulse of electricity. Within moments, the calm dissolves into motion as the fish converge, their movements synchronized by hunger and competition. When the frenzy subsides, only drifting fragments remain, sinking slowly into the depths to nourish the river's unseen life. Above, the rainforest breathes, sustained by the nutrients carried from this fleeting storm of predation. In this silent exchange between hunger and renewal, the anomaly reveals its truth with unmistakable clarity. The river does not merely flow. It acts. It reshapes the world. Across tropical coastlines and coral reef systems, the stability of entire benthic communities can hinge upon the relentless blows of a predator no longer than a human hand. The mantis shrimp, a creature armed with the fastest known strike in the animal kingdom, has altered the architecture of reef ecosystems by controlling populations of mollusks, crabs, and other armored invertebrates. Where it thrives, shells fracture, prey distributions shift, and the delicate balance of reef biodiversity adjusts to the rhythms of its violence. When food becomes scarce, this solitary hunter escalates its aggression, delivering repeated strikes with devastating speed and force. These bursts of predation reverberate through coral ecosystems, influencing nutrient cycles, shaping species composition, and reinforcing the fragile equilibrium upon which tropical reefs depend. The anomaly of the mantis shrimp lies not merely in the power of its weaponry, but in the relentless urgency of hunger, a biological pressure that transforms territorial defense into a high-stakes gamble for survival. The mechanism behind this extraordinary capability resides within a specialized appendage known as the raptorial limb, a structure evolved into either a piercing spear or a smashing club, depending on the species. In smashers, such as the iconic peacock mantis shrimp, the appendage functions as a biological hammer powered by a complex spring and latch system embedded within layers of mineralized chitin and crystalline hydroxyapatite. This composite structure stores elastic energy and releases it with explosive acceleration, propelling the club forward with such velocity that it generates cavitation bubbles, imploding shockwaves capable of stunning or killing prey even when the initial strike misses its target. The force produced rivals that of a projectile discharged from a firearm, yet it is executed with precision measured in fractions of a second. Complementing this mechanical prowess is a visual system unparalleled in the animal kingdom, equipped with an array of photoreceptors capable of detecting polarized and multispectral light. These eyes allow the mantis shrimp to identify prey, rivals, and territorial boundaries with extraordinary clarity, ensuring that each strike is both deliberate and efficient. Under stable conditions, mantis shrimp maintain solitary territories within coral rubble or burrows carved into reef substrates, emerging cautiously to hunt passing prey. Their metabolism, though efficient, demands a steady intake of energy to sustain the maintenance of their powerful appendages and complex sensory systems. Hunger disrupts this balance, triggering a behavioral escalation that transforms cautious ambush into aggressive pursuit. As prey becomes scarce due to seasonal shifts, environmental stress, or ecological competition, the mantis shrimp increases the frequency of its attacks, delivering rapid successive strikes against armored mollusks and crustaceans. Each blow carries an energetic cost, requiring precise muscular coordination and the reloading of the spring mechanism within the raptorial limb. Repeated strikes intensify metabolic expenditure, forcing the animal into a cycle where success must be achieved swiftly or the cost of failure will erode its strength. This escalation introduces a precarious trade-off between aggression and vulnerability. While the mantis shrimp's weaponry grants it formidable predatory dominance, the repeated delivery of high-velocity strikes exposes the appendage to structural fatigue and potential fracture. Studies have revealed microscopic damage accumulating within the impact region of the club, evidence of the immense forces generated during each blow. Although the composite architecture of the limb provides remarkable resistance to wear, hunger-driven aggression amplifies the risk of injury, transforming every attack into a gamble between nourishment and self-destruction. The predator must succeed quickly or weaken, illustrating a biological paradox in which survival depends upon the careful balance between power and endurance. The ecological consequences of this risk-driven aggression extend outward in complex and far-reaching cascades. By regulating populations of shellfish and crustaceans, mantis shrimp influence the composition of reef communities and the distribution of benthic organisms. Their predation prevents the overabundance of grazing invertebrates that might otherwise destabilize coral substrates or outcompete other species for limited resources. In regions where mantis shrimp densities increase during periods of prey scarcity, their intensified feeding pressure alters local biodiversity, reshaping the structure of reef ecosystems and influencing the availability of habitat for juvenile fish and invertebrates. Each strike against a shell reverberates through the ecosystem, redistributing energy and maintaining the dynamic equilibrium of coral habitats. These localized impacts scale upward to affect broader marine processes, including nutrient cycling and reef resilience. The fragmentation of shells and exoskeletons generated by mantis shrimp feeding contributes to the formation of calcareous sediments, which stabilize reef foundations and provide substrate for coral growth. This continual breakdown and redistribution of skeletal material supports the long-term persistence of reef structures, enabling them to withstand environmental stresses such as storm surges and rising sea temperatures. In this way, the aggression of a solitary predator contributes indirectly to the maintenance of coastal ecosystems that buffer shorelines, nurture biodiversity, and sustain fisheries essential to human survival. Human civilization intersects with this anomaly through the ecological services provided by coral reefs, shaped in part by mantis shrimp predation. These reefs support a substantial proportion of global marine biodiversity and underpin fisheries that feed millions of people. By regulating populations of shellfish and crustaceans, mantis shrimp help preserve the balance necessary for reef productivity and resilience. The calcareous sediments produced through their feeding activities contribute to the structural integrity of reef systems that protect coastal communities from erosion and storm damage. Moreover, the remarkable mechanical properties of their raptorial appendages have inspired advances in materials science, influencing the development of impact-resistant composites used in engineering, medicine, and protective technologies. Thus, the mantis shrimp's aggression extends beyond ecological influence into the realm of human innovation, illustrating the profound interconnectedness of biological adaptation and technological progress. A new layer of ecological complexity emerges as hunger-driven aggression alters the mantis shrimp's spatial behavior. Under conditions of scarcity, individuals expand their foraging ranges, venturing beyond established territories and engaging in more frequent encounters with rivals. These confrontations intensify competition and elevate the risk of injury, as territorial disputes are resolved through ritualized displays or direct combat. The resulting redistribution of individuals reshapes the spatial dynamics of reef communities, influencing patterns of predation and competition that cascade through the ecosystem. Such behavioral shifts highlight the delicate balance between territorial stability and ecological adaptability, revealing how hunger can transform a solitary predator into an agent of broader environmental change. The intersection of these ecological dynamics with climate change introduces further tension into the narrative. Rising ocean temperatures and increasing acidity threaten coral reef ecosystems, reducing the availability of prey and intensifying the pressures that drive mantis shrimp aggression. As environmental stresses disrupt the delicate balance of reef habitats, the frequency and intensity of predatory strikes may increase, amplifying the energetic demands placed upon these animals. Simultaneously, the degradation of coral structures diminishes the availability of shelter and hunting grounds, exposing mantis shrimp to heightened vulnerability. In this context, the predator's extraordinary power becomes both a lifeline and a liability, enabling survival while exacting a heavy physiological toll. An unexpected twist reframes the mantis shrimp's formidable reputation. Despite its extraordinary strength and sensory sophistication, this predator remains acutely sensitive to environmental disturbance. Habitat degradation, pollution, and ocean acidification threaten the integrity of coral reefs upon which it depends, undermining the stability of its territories and reducing the abundance of prey. The same appendage, capable of shattering shells with explosive force, cannot shield the animal from the silent erosion of its habitat. As reef ecosystems decline, the mantis shrimp's aggressive strategy becomes increasingly unsustainable, forcing it into ever riskier encounters that heighten the probability of injury and mortality. The anomaly thus reveals itself as fragile beneath its veneer of invincibility, a predator whose survival is inseparable from the health of the ecosystems it helps shape. This fragility underscores a broader ecological truth. The stability of coral reefs and the human communities that depend upon them is intimately linked to the actions of organisms operating at scales often overlooked. The repeated strikes of a mantis shrimp fracture shells, redistribute nutrients, and contribute to the formation of sediments that anchor reef systems against the forces of erosion and climate change. These processes sustain biodiversity, support fisheries, and protect coastlines from the encroaching sea. In this intricate web of cause and consequence, the mantis shrimp emerges not merely as a predator, but as a catalyst of resilience, its aggression woven into the fabric of marine ecosystems and human livelihoods alike. As hunger intensifies and aggression escalates, the mantis shrimp becomes trapped within a cycle of necessity and risk. Each strike demands energy, each failure erodes strength, and each confrontation with prey or rival carries the potential for injury. Success must come swiftly, for prolonged struggle threatens to weaken the predator and compromise its ability to defend territory or capture food. This relentless calculus of survival reveals the paradox at the heart of the anomaly. Power, when driven by hunger, becomes both weapon and burden, a force capable of sustaining life while simultaneously courting destruction. In the final image, the reef lies suspended in crystalline water, its labyrinth of coral and rubble illuminated by shafts of sunlight descending from the surface. Within a narrow burrow, a mantis shrimp waits, its iridescent carapace shimmering with spectral hues as its compound eyes scan the shifting currents. Hunger stirs, compelling the predator from its refuge into the open world beyond. With explosive precision, the raptorial limb strikes, shattering a shell in a burst of force that echoes through the surrounding reef. Fragments drift downward, settling into the sediment that will one day form the foundation of new coral growth. Beneath the waves, ecosystems adjust, coastlines endure, and human futures remain tethered to the silent violence of this extraordinary hunter. In that fleeting instant of impact, the anomaly reveals its truth with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Entire coastal ecosystems have shifted in response to a predator whose intelligence rewrites the rules of survival, reshaping marine food webs and influencing the stability of fisheries across the globe. Dolphins, far from being passive inhabitants of the sea, have altered ecological dynamics through adaptive hunting strategies that emerge when resources grow scarce. In regions where prey declines, these marine mammals transform hunger into innovation, inventing new techniques that redistribute fish populations, reorganize predator-prey relationships, and ripple outward into coastal economies and climate-regulating ecosystems. Their behavioral plasticity has allowed them to thrive across diverse marine environments, from estuaries and coral reefs to the open ocean, altering ecological balances through ingenuity rather than brute force. The anomaly of dolphins lies not in their speed or strength, but in their capacity to invent, to cooperate, and to adapt when survival is threatened. demonstrating that intelligence itself can become an ecological force with planetary consequences. The biological foundation of this phenomenon resides in a nervous system of extraordinary complexity. Dolphins possess large, intricately folded brains with expanded neocortical regions that support advanced cognition, memory, and social learning. Their encephalization quotient ranks among the highest of any animal, enabling them to process sensory information with remarkable sophistication and to develop intricate behavioral repertoires. Echolocation, generated through specialized nasal passages and transmitted via the melon, allows dolphins to perceive their environment in acoustic detail, constructing three-dimensional auditory maps of prey, obstacles, and fellow pod members. This sensory precision is coupled with acute hearing and refined motor coordination, permitting rapid maneuverability and synchronized group movement. Under stable conditions, dolphins employ efficient hunting strategies that rely on speed, communication, and cooperation, corralling fish into dense schools before striking with calculated precision. Yet, these strategies, while effective, are not fixed. They evolve in response to environmental pressures that demand innovation. When prey becomes scarce due to overfishing, climate-driven shifts, or habitat degradation, dolphins confront a challenge that reshapes their behavior and social structure. Hunger disrupts established routines, compelling pods to experiment with novel hunting techniques that expand their ecological reach. Among the most striking of these adaptations is mud ring feeding, a strategy observed in shallow coastal waters where dolphins circle their prey while beating their tails against the sea floor, creating a rising plume of sediment. This swirling barrier traps fish within a cylindrical wall of mud, forcing them to leap into open water where waiting dolphins capture them with effortless precision. Such innovation reflects not instinct alone, but learned behavior transmitted through social networks, illustrating how necessity catalyzes creativity within the marine environment. This expansion of hunting strategies triggers cascading ecological consequences that reverberate through marine ecosystems. By altering prey distributions and exploiting new habitats, dolphins influence the structure of fish populations and reshape trophic interactions across coastal regions. In estuaries where cooperative trapping techniques concentrate fish near shorelines, nutrient cycles shift as prey species redistribute their feeding patterns and migratory routes. These changes ripple outward to affect plankton communities, benthic invertebrates, and the productivity of seagrass meadows and coral reefs. Each innovative hunting event reshapes the flow of energy through the ecosystem, demonstrating how behavioral adaptation can reverberate through biological networks with far-reaching implications. A new dimension of ecological influence emerges as dolphins refine cooperative hunting strategies that amplify their impact on marine food webs. In certain regions, pods employ coordinated tactics such as wave washing, herding fish towards sandbanks, or driving prey into confined spaces where escape becomes impossible. These techniques require precise communication, synchronized movement, and shared knowledge passed between generations. The resulting predation pressure regulates fish populations and prevents the overabundance of certain species that might otherwise destabilize local ecosystems. Through these collective behaviors, dolphins function as architects of ecological balance, their intelligence shaping the composition and resilience of marine habitats across vast geographic ranges. The cascading effects extend beyond the immediate realm of predator and prey, influencing coastal ecosystems and the services they provide. By regulating fish populations that graze upon seagrass and coral reefs, dolphins contribute indirectly to the health of these habitats, which serve as nurseries for countless marine species and as buffers against coastal erosion. Seagrass meadows and coral reefs also act as significant carbon sinks, absorbing and storing atmospheric carbon dioxide while supporting biodiversity essential to ocean productivity. In this intricate network of ecological interactions, the adaptive hunting strategies of dolphins contribute to the maintenance of habitats that stabilize coastlines, protect marine biodiversity, and sustain the global climate system. Human civilization intersects with these dynamics in profound and multifaceted ways. Coastal fisheries, which provide sustenance and livelihoods for millions of people, depend upon the stability of marine ecosystems shaped in part by dolphin predation. By regulating fish populations and influencing migratory patterns, dolphins contribute to the sustainability of fisheries that underpin regional economies and global markets. Their presence also shapes ecotourism industries, drawing visitors to coastal regions and fostering conservation initiatives that support both marine biodiversity and human livelihoods. In this context, the behavioral innovations of dolphins transcend ecological significance, intersecting with economic systems and cultural traditions that reflect humanity's enduring connection to the ocean. Beyond their ecological and economic roles, dolphins have influenced human understanding of intelligence, communication, and cooperation, inspiring scientific inquiry and technological innovation. Research into their echolocation has contributed to advancements in sonar technology, medical imaging, and acoustic engineering, illustrating how biological adaptations can inform human progress. The expansion of dolphin hunting strategies under environmental pressure offers insights into cognitive flexibility and cultural transmission, revealing parallels between human ingenuity and the adaptive behaviors of marine mammals. These connections underscore the profound interdependence between human civilization and the living systems of the ocean, where survival and innovation are inextricably linked. An unexpected twist reframes the narrative of dolphin resilience. Despite their intelligence and adaptability, dolphins remain vulnerable to environmental degradation, pollution, and climate change. Declining fish populations, habitat loss, and the accumulation of toxins within marine food webs threaten their survival, undermining the very conditions that foster behavioral innovation. The same intelligence that enables dolphins to adapt to scarcity also exposes them to increasing risks as they venture into unfamiliar or degraded habitats in search of food. This paradox reveals a fragile equilibrium in which the success of these remarkable predators depends upon the stability of the ecosystems they help sustain. The decline of dolphin populations carries profound ecological and societal consequences. As apex predators and cooperative hunters, their absence can disrupt food webs, allowing prey populations to expand unchecked and destabilize marine ecosystems. Such imbalances can lead to declines in fish stocks, degradation of coral reefs and seagrass meadows, and diminished resilience of coastal habitats against the forces of climate change. For human communities dependent upon fisheries and coastal resources, the loss of dolphins represents not merely a biological tragedy, but an economic and environmental crisis, underscoring the intricate connections between marine life and human survival. As environmental pressures intensify across the world's oceans, the adaptive hunting strategies of dolphins become increasingly vital to the resilience of marine ecosystems. Rising sea temperatures, shifting currents, and overexploitation of marine resources compel dolphins to innovate continually, refining techniques that enable them to navigate a rapidly changing environment. Each new strategy reflects a delicate balance between energy expenditure and survival, demonstrating that intelligence becomes more valuable under pressure. In this dynamic interplay between necessity and adaptation, dolphins emerge as living testaments to the power of behavioral evolution in shaping ecological outcomes. The culmination of this anomaly unfolds in the shimmering waters of a coastal estuary at dawn. A pod of dolphins glides silently through the shallows, their movements synchronized with effortless precision. As hunger presses upon them, one dolphin sweeps its tail across the sea floor, raising a curtain of sediment that encircles a school of fish in a rising wall of mud. The trapped prey leap into the air, and the pod surges forward in coordinated harmony, capturing each fish with calculated grace. Beneath the surface, nutrients disperse. Prey populations adjust, and the rhythm of the ecosystem shifts in response to this fleeting moment of ingenuity. In the stillness that follows, the water settles, carrying the echoes of innovation through the currents. The anomaly reveals itself with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Across tropical and subtropical oceans, entire reef communities have been reshaped by a predator that seldom leaves the shadows, yet whose presence determines the balance of life beneath the waves. When moray eels emerge from their hidden crevices in search of food, their actions reverberate through coral ecosystems, altering prey populations, redistributing nutrients, and influencing the resilience of reefs that protect coastlines and sustain fisheries. Their decisions, dictated by hunger and necessity, have silently sculpted marine biodiversity for millions of years. In regions where morays decline or shift their behavior, the delicate equilibrium between predator and prey destabilizes, triggering cascading consequences that ripple outward into coastal economies and climate-regulating habitats. The anomaly of the moray eel lies not in constant aggression, but in the moments when scarcity forces it to abandon safety, transforming a reclusive ambush predator into an exposed hunter whose movements reshape the reef and echo far beyond it. The biological mechanism behind this transformation begins with an anatomy uniquely suited for life within narrow refuges. Moray eels possess elongated, muscular bodies devoid of pectoral fins, allowing them to navigate labyrinthine coral structures with serpentine precision. Their skin secretes a protective mucus layer that shields against abrasion and infection, while enabling effortless movement through confined spaces. Most extraordinary, however, is their double-jawed feeding apparatus. In addition to their primary jaws, morays possess a set of pharyngeal jaws located within the throat, capable of lunging forward to grasp and draw prey into the esophagus. This evolutionary adaptation compensates for the eel's inability to generate suction, ensuring that captured prey cannot escape even within the tight confines of a crevice. Equipped with acute olfactory receptors and sensitive lateral line systems, moray eels detect chemical cues and vibrations in the surrounding water, enabling them to locate prey while remaining concealed. Under stable conditions, these adaptations allow them to hunt efficiently without exposing themselves to unnecessary risk, preserving energy while maintaining dominance within their chosen territories. When prey becomes scarce, however, the balance between concealment and survival begins to fracture. Environmental changes, seasonal fluctuations, and human exploitation can diminish the availability of fish and crustaceans, that sustain moray populations. Hunger intensifies metabolic demands, compelling these reclusive predators to venture beyond the protective confines of their dens. Emerging into open water, moray eels abandon the security of coral crevices and patrol reef slopes, seagrass meadows, and sandy substrates in search of sustenance. This shift in behavior represents a profound trade-off, as the eel's elongated body and ambush-oriented hunting strategy leave it more vulnerable to larger predators such as sharks, groupers, and barracudas. Hunger thus transforms caution into risk, forcing the moray into environments where success promises survival, yet exposure invites danger. This departure from safety initiates a cascade of ecological consequences that ripple through reef ecosystems. As moray eels expand their hunting territories, they exert predation pressure on fish populations that might otherwise proliferate unchecked. By consuming mid-level predators and herbivores, morays influence the distribution of species that regulate algal growth and maintain coral health. In regions where moray activity intensifies due to prey scarcity, shifts in fish populations alter grazing patterns, affecting the balance between coral and algae. Such changes reverberate through the reef, influencing habitat complexity, biodiversity, and the stability of ecosystems that serve as nurseries for countless marine organisms. The eel's decision to leave its refuge becomes a catalyst for transformation, reshaping the intricate web of interactions that sustains coral reef environments. A surprising dimension of this ecological role emerges through the moray's participation in cooperative hunting with other predators. In certain reef systems, moray eels have been observed collaborating with groupers in a remarkable display of interspecies coordination. The grouper signals the moray through specific movements, guiding it toward hidden prey within crevices where the eel's serpentine body can penetrate. When hunger drives morays into open water, these partnerships become more frequent, amplifying predation efficiency and redistributing prey populations across the reef. This cooperative behavior not only enhances hunting success, but also illustrates the complex social dynamics that arise when environmental pressures demand innovation. The resulting shifts in prey distribution reverberate throughout the ecosystem, influencing biodiversity and reinforcing the delicate equilibrium upon which reef communities depend. As these cascading effects intensify, their influence extends beyond the confines of the reef to encompass coastal ecosystems and climate regulation. Coral reefs shaped by the predatory activities of moray eels serve as natural barriers that dissipate wave energy, protecting shorelines from erosion and storm surges. These habitats also support seagrass meadows and mangrove forests that capture and store significant quantities of carbon, contributing to the regulation of global climate systems. By influencing fish populations and maintaining ecological balance, moray eels play an indirect yet vital role in sustaining the resilience of these interconnected habitats. Each venture into open water, driven by hunger, reverberates through the reef's biological architecture, reinforcing the stability of coastal ecosystems that safeguard both biodiversity and human communities. Human civilization is intricately entwined with these dynamics. Coral reefs, influenced by moray eel predation, support fisheries that provide food and livelihoods for millions of people worldwide. The health of reef ecosystems determines the productivity of fish populations that sustain coastal economies and global markets. In regions where morays expand their hunting ranges due to prey scarcity, shifts in fish distributions can influence catch yields, altering the economic stability of fishing communities. Additionally, the reefs preserved through balanced predator-prey relationships attract tourism, generating revenue that supports conservation initiatives and fosters a deeper appreciation for marine biodiversity. The actions of a solitary eel, compelled by hunger to abandon its refuge, thus intersect with human survival, shaping economies and reinforcing the interconnectedness of ecological and societal systems. Beyond economic influence, moray eels contribute to nutrient cycling within reef ecosystems, further linking their behavior to environmental resilience. As opportunistic predators and scavengers, they consume carrion and wounded organisms, accelerating the decomposition process and redistributing organic matter throughout the reef. This rapid recycling of nutrients fuels microbial communities, supports plankton growth, and sustains the productivity of marine food webs that extend from the seafloor to the surface. The eel's emergence from its den in times of scarcity amplifies this ecological function, ensuring that energy flows efficiently through the ecosystem. Such processes underpin the health of coral reefs and adjacent habitats, reinforcing their capacity to withstand environmental stresses and climate change. An unexpected twist emerges from the moray eel's formidable yet fragile existence. Despite their fearsome appearance and specialized adaptations, moray eels are highly sensitive to environmental degradation and habitat loss. Coral bleaching, pollution, and overfishing threaten the structural complexity of reefs that provide essential shelter and hunting grounds. As these habitats deteriorate, morays are forced into open water with increasing frequency, exposing them to predation and reducing their chances of survival. The very behavior that enhances their hunting success under conditions of scarcity becomes a liability in degraded environments, revealing a paradox at the heart of their anomaly. The predator that shapes reef ecosystems through calculated risk is itself vulnerable to the silent erosion of the habitats upon which it depends. This fragility reframes the moray eel's ecological significance, highlighting the delicate balance between survival and exposure. Their decline could trigger cascading effects that destabilize reef communities, allowing prey populations to expand unchecked and altering the distribution of species that maintain coral health. Such imbalances would compromise the resilience of reef ecosystems, diminishing their capacity to protect coastlines, support fisheries, and regulate global carbon cycles. In this context, the moray eel emerges not merely as a reclusive predator, but as a sentinel of ecological stability, its survival intertwined with the health of marine environments and the future of human societies. As environmental pressures intensify and prey availability fluctuates, the moray eel's departure from its safe zone becomes increasingly frequent, amplifying both its ecological influence and its vulnerability. Each venture into open water represents a negotiation between safety and survival, a biological calculus shaped by hunger and necessity. The eel's serpentine form glides across the reef, navigating a landscape fraught with risk, yet rich with opportunity. In this silent exchange between predator and environment, the moray eel embodies the tension between resilience and fragility, revealing how the forces of scarcity can transform even the most secretive hunter into an agent of ecological change. The final image unfolds beneath a twilight sea, where coral towers rise like ancient citadels and currents shimmer with suspended light. From the shadowed entrance of a narrow crevice, a moray eel emerges, its sinuous body undulating through the open water with deliberate precision. Hunger guides its path, compelling it beyond the sanctuary of stone into a realm where predators roam and prey scatter. With a sudden strike, its jaws close upon a passing fish, and the pharyngeal jaws surge forward to secure the catch. In that fleeting moment, energy flows through the reef, nutrients are redistributed, and the delicate balance of life adjusts in response. The eel retreats into darkness, leaving behind ripples that echo through ecosystems, coastlines, and human livelihoods. Within this silent transaction between risk and survival, the anomaly reveals its truth with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Across the vast pelagic highways of the world's oceans, the relentless migrations of tuna have reshaped marine ecosystems, influenced global fisheries, and altered the trajectory of human history. These powerful predators, moving in immense schools across entire ocean basins, dictate the distribution of prey species, regulate food webs, and sustain one of the largest and most valuable fisheries on Earth. When food becomes scarce, tuna extend their migrations and intensify their pursuit of prey, forcing ecosystems and economies to adapt to their movements. Their presence influences nutrient transport across hemispheres, linking distant marine regions through biological corridors that redistribute energy and sustain ocean productivity. The anomaly of tuna lies not merely in their speed or strength, but in their endurance, for hunger compels them into epic journeys where survival hinges on the outcome of each pursuit, transforming the open ocean into a theater of constant risk and consequence. The biological machinery that enables this extraordinary lifestyle is among the most sophisticated in the marine realm. Tuna possess a streamlined, torpedo-shaped body engineered for sustained high-speed swimming, minimizing drag while maximizing efficiency across immense distances. Unlike most fish, they exhibit regional endothermy, a physiological adaptation that allows them to maintain elevated body temperatures through a countercurrent heat exchange system known as the rete mirabile. This specialized network of blood vessels conserves metabolic heat generated by powerful swimming muscles, enabling tuna to operate with remarkable efficiency in cold, nutrient-rich waters where prey is abundant. Their rigid, crescent-shaped tails and retractable fins reduce turbulence and enhance hydrodynamic performance, while large, oxygen-rich gills support the intense metabolic demands of continuous motion. This unique combination of anatomical and physiological traits transforms tuna into endurance athletes of the sea, capable of traversing entire ocean basins in pursuit of sustenance. Under stable conditions, these predators exploit dense aggregations of prey such as sardines, anchovies, and squid, coordinating their movements with seasonal currents and oceanographic features. However, environmental variability and overexploitation of forage fish can disrupt these predictable patterns, forcing tuna to travel greater distances and expend more energy in search of food. Hunger intensifies the stakes of each hunt, compelling them to chase elusive prey across open waters where success is uncertain. Unlike ambush predators that rely on stealth, tuna depend on relentless pursuit, maintaining high velocities for extended periods as they drive prey into tightly packed schools. Each failed chase carries a physiological cost, rapidly depleting energy reserves and threatening survival. In these moments of scarcity, endurance becomes not merely advantageous, but essential, as the balance between caloric expenditure and nutritional gain determines whether the predator thrives or weakens. The ecological consequences of this long-distance pursuit ripple across marine ecosystems with profound intensity. As tuna expand their migratory routes in response to prey scarcity, they exert predation pressure on forage fish populations across vast regions of the ocean. These shifts influence the distribution of plankton, zooplankton, and small pelagic fish that form the foundation of marine food webs. When tuna populations intensify predation in certain areas, prey species redistribute, altering nutrient cycling and primary productivity across entire ocean basins. Such changes reverberate through ecosystems, influencing the abundance of seabirds, marine mammals, and other apex predators that depend upon the same resources. In this way, the pursuit of a single meal by a migrating school of tuna can reshape the biological architecture of the pelagic realm. A surprising escalation emerges as tuna act as vectors of nutrient transport, linking distant ecosystems through their migrations. By feeding in nutrient-rich regions and excreting waste in oligotrophic waters, they redistribute essential elements such as nitrogen and phosphorus across the ocean, enhancing productivity in otherwise nutrient-poor environments. This biological pump contributes to the stability of marine ecosystems, sustaining phytoplankton communities that generate a significant portion of the planet's oxygen. As tuna travel farther in search of prey during periods of scarcity, their role in nutrient redistribution intensifies, amplifying their influence on global biogeochemical cycles. Hunger thus transforms these predators into agents of planetary connectivity, bridging ecosystems separated by thousands of kilometers and reinforcing the delicate equilibrium of the ocean's life support systems. The cascading effects of tuna migration extend to coastal ecosystems and climate regulation. By controlling populations of forage fish, tuna indirectly influence the grazing pressure exerted on plankton communities, which play a critical role in carbon sequestration. Phytoplankton, sustained by the nutrient flows shaped by tuna migrations, absorb atmospheric carbon dioxide and contribute to the regulation of global climate systems. In regions where tuna populations decline or alter their migratory patterns, disruptions in these processes can reverberate through marine ecosystems, diminishing productivity and destabilizing carbon cycles. The endurance-driven pursuits of tuna, therefore, resonate far beyond the immediate act of predation, influencing the resilience of ecosystems that regulate Earth's climate and sustain biodiversity. Human civilization is intimately entwined with these dynamics, as tuna fisheries represent one of the most significant sources of protein and economic activity in the global seafood market. The migratory patterns of tuna dictate the fortunes of fishing communities, shaping trade routes, international agreements, and cultural traditions across continents. As tuna travel farther in search of prey, fishing fleets must follow, expanding their range into remote waters and intensifying competition for dwindling resources. The success or failure of a tuna's pursuit thus reverberates through global markets, influencing food security, employment, and the stability of coastal economies. Hunger-driven migrations not only determine the survival of the predator, but also shape the livelihoods of millions who depend upon the bounty of the sea. Beyond economic influence, tuna have played a pivotal role in the advancement of marine science and technology. Their remarkable physiological adaptations have inspired research into hydrodynamics, bioenergetics, and thermal regulation, informing innovations in engineering, medicine, and environmental monitoring. Satellite tracking of tuna migrations has revealed the interconnectedness of oceanic ecosystems, providing critical insights into climate change, ocean currents, and the distribution of marine life. These discoveries underscore the profound relationship between human understanding and the biological phenomena embodied by tuna, illustrating how the pursuit of prey across vast distances has illuminated the hidden dynamics of the world's oceans. An unexpected twist reframes the narrative of endurance and dominance. Despite their extraordinary capabilities, tuna are profoundly vulnerable to environmental change and overexploitation. Intensive fishing pressure, habitat degradation, and climate-driven shifts in ocean temperature and productivity threaten their populations, disrupting the migratory patterns that sustain marine ecosystems and global fisheries. The very traits that enable tuna to traverse immense distances in search of food also expose them to exploitation across international waters, rendering them susceptible to population declines that reverberate throughout the ocean. As prey scarcity intensifies and environmental conditions fluctuate, the margin between survival and collapse narrows, revealing the fragility beneath their formidable endurance. This vulnerability introduces a new tension into the ecological narrative, as the decline of tuna populations could destabilize marine food webs and disrupt the biogeochemical cycles they help sustain. Without the regulating influence of these apex predators, forage fish populations may expand unchecked, altering plankton dynamics and diminishing the productivity of ecosystems upon which countless species and human communities depend. The loss of tuna would not merely remove a predator from the ocean, but would unravel a complex network of interactions that support fisheries, regulate climate, and sustain the delicate balance of life across the pelagic realm. Hunger-driven pursuit, once a symbol of resilience, becomes a reminder of the precarious equilibrium upon which both predator and planet depend. As environmental pressures intensify and prey distributions shift, the endurance of tuna becomes increasingly critical to their survival and to the stability of marine ecosystems. Rising ocean temperatures, changing currents, and the depletion of forage fish compel these predators to travel farther and expend greater energy in search of sustenance. Each pursuit becomes a high-stakes decision, a calculation of risk and reward where failure can lead to rapid energy loss and declining strength. In this relentless calculus of survival, the ocean becomes both pathway and proving ground, demanding resilience from those who traverse its boundless expanse. The final image unfolds in the cobalt depths of the open sea, where a school of tuna glides through sunlit waters with unwavering determination. Their bodies flash like living steel as they surge forward in pursuit of a distant shoal of fish, each movement synchronized with the currents that guide their migration. Hunger propels them onward, transforming the ocean into a vast arena of endurance where success sustains life and failure invites decline. Beneath their passage, nutrients disperse, ecosystems adjust, and the rhythms of the pelagic world continue to unfold. In this silent drama of pursuit and survival, the anomaly reveals its truth with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Entire coastlines have been quietly reshaped by a creature whose influence rarely attracts attention, yet whose opportunism determines the fate of marine ecosystems across the globe. From tidal marshes and mangrove forests to coral reefs and abyssal plains, crabs function as relentless recyclers, dismantling the remains of life and redistributing energy through the ocean's intricate food webs. Their scavenging behavior accelerates decomposition, regulates disease, and fuels nutrient cycles that sustain fisheries, stabilize coastlines, and influence global carbon storage. When food becomes scarce, these seemingly passive crustaceans transform into active opportunists, pursuing weakened prey and exploiting any available resource. In such moments, the environment becomes a battlefield of chance, where survival depends upon seizing opportunity before rivals intervene. The anomaly of the crab lies not in dominance or speed, but in adaptability, for hunger converts restraint into aggression, reshaping ecosystems through a cascade of consequences that extend far beyond the shoreline. The biological mechanism underlying this transformation begins with an anatomy uniquely suited for opportunistic feeding. Crabs possess a hardened exoskeleton composed of chitin reinforced with calcium carbonate, providing protection while serving as a framework for powerful musculature. Their chelae, or pincers, vary widely in form and function, ranging from delicate instruments capable of manipulating detritus to formidable crushing claws designed to fracture shells and dismember prey. Beneath this armored exterior lies a sophisticated sensory network attuned to chemical cues and vibrations in the water, enabling crabs to detect traces of decay, injury, or movement across considerable distances. Their compound eyes, perched atop mobile stalks, grant a panoramic field of vision that enhances vigilance and spatial awareness. Under stable conditions, these adaptations support a largely scavenging lifestyle, allowing crabs to consume carrion, algae, and organic debris while conserving energy and minimizing risk. When hunger intensifies and resources diminish, the crab's behavior shifts from passive scavenging to active opportunism. Environmental stresses such as tidal fluctuations, seasonal scarcity, and habitat degradation can reduce the availability of detritus and plant matter, compelling crabs to expand their dietary range. In these moments, they become aggressive hunters, targeting weakened fish, mollusks, and other invertebrates unable to escape their grasp. Their claws, once instruments of cautious feeding, transform into tools of decisive predation, capable of crushing shells and severing appendages with remarkable efficiency. This transition reflects an evolutionary strategy shaped by uncertainty, where adaptability ensures survival in dynamic environments characterized by competition and scarcity. The consequences of this opportunistic shift reverberate through marine ecosystems with remarkable intensity. By consuming carrion and weakened organisms, crabs accelerate the decomposition process, redistributing nutrients that fuel microbial activity and sustain plankton communities. These nutrient pulses enhance primary productivity, supporting the growth of phytoplankton that form the foundation of marine food webs and contribute significantly to global oxygen production. As crabs intensify their feeding under conditions of scarcity, their role as ecological recyclers becomes amplified, reinforcing the resilience of coastal and benthic ecosystems. Each scavenged carcass becomes a conduit of energy, linking life and death in a continuous cycle that sustains biodiversity across the ocean's vast expanse. A surprising escalation emerges as crab populations influence the structure and stability of coastal habitats. In mangrove forests and salt marshes, burrowing crabs aerate sediments and regulate the distribution of organic matter, enhancing soil fertility and promoting the growth of vegetation that stabilizes shorelines. These habitats serve as nurseries for countless marine species and act as buffers against storm surges and erosion. When hunger drives crabs to intensify their foraging activities, their burrowing and feeding behaviors accelerate nutrient cycling and sediment turnover, shaping the physical and biological architecture of coastal ecosystems. The opportunistic pursuit of food thus extends beyond individual survival, reinforcing the integrity of habitats that protect both marine biodiversity and human communities. The ripple effects of crab opportunism extend into coral reef ecosystems, where their predation on weakened invertebrates influences species composition and ecological balance. By targeting injured or diseased organisms, crabs reduce the spread of pathogens and prevent the accumulation of decaying biomass that could destabilize reef environments. This natural sanitation service contributes to the health and resilience of coral communities, supporting biodiversity and sustaining the productivity of reef-based fisheries. In times of scarcity, the crab's opportunistic behavior intensifies, transforming it into a dynamic regulator of ecosystem stability whose actions reverberate through the intricate web of marine life. Human civilization is deeply intertwined with these ecological processes. Coastal fisheries, aquaculture operations, and global seafood markets rely on the productivity of ecosystems shaped in part by crab populations. Many species of crab represent vital sources of protein and economic revenue, supporting livelihoods and cultural traditions across continents. Their scavenging and predatory activities influence the abundance of commercially valuable shellfish and fish species, shaping harvest yields and market dynamics. In regions where crab populations expand or shift their feeding behavior due to environmental pressures, the resulting ecological changes can impact food security, economic stability, and the sustainability of marine resources upon which millions depend. Beyond their economic significance, crabs contribute to coastal protection and climate regulation through their influence on habitat stability and carbon sequestration. Mangroves, seagrass meadows, and salt marshes shaped by crab activity store vast quantities of carbon within their sediments, mitigating the effects of climate change while safeguarding shorelines from erosion and rising sea levels. By aerating soils and redistributing organic matter, crabs enhance the productivity and resilience of these ecosystems, reinforcing their role as natural defenses against environmental stresses. The opportunistic feeding strategies of crabs, driven by hunger and environmental variability, thus intersect with global climate systems and human survival, illustrating the profound interconnectedness of marine life and planetary health. An unexpected twist emerges from the very adaptability that defines the crab's ecological success. Despite their resilience and versatility, many crab species are vulnerable to environmental degradation, overharvesting, and climate change. Ocean acidification threatens the integrity of their calcium carbonate exoskeletons, weakening their defenses and impairing their ability to forage effectively. Habitat destruction, pollution, and rising sea temperatures further disrupt their populations, altering the delicate balance between scavenging and predation that sustains marine ecosystems. In certain regions, invasive crab species have expanded beyond their native ranges, reshaping local habitats and outcompeting native fauna. This duality reveals a complex paradox in which the opportunistic strategies that enable crabs to thrive under scarcity also render them susceptible to ecological instability and environmental upheaval. The fragility of crab populations introduces new tension into the ecological narrative, as their decline or proliferation can trigger cascading effects across marine and coastal systems. The loss of native crab species may disrupt nutrient cycling and sediment stability, undermining the resilience of habitats that protect coastlines and support fisheries. Conversely, the expansion of invasive crabs can alter food webs, degrade habitats, and diminish biodiversity, reshaping ecosystems in unpredictable ways. In both scenarios, the opportunistic nature of the crab becomes a force of transformation, demonstrating how the balance between scavenging and predation can influence the trajectory of ecological and human systems alike. As environmental pressures intensify and resources fluctuate, the opportunistic behavior of crabs becomes increasingly pronounced, amplifying their influence on marine ecosystems. Hunger compels them to seize every available opportunity, transforming tranquil tidal flats and reef crevices into arenas of relentless competition. Each scavenged carcass and captured prey redistributes energy through the food web, sustaining the productivity of habitats that support biodiversity, regulate climate, and provide nourishment for human populations. In this dynamic interplay between scarcity and survival, the crab emerges as both recycler and predator, its actions shaping the resilience of ecosystems that underpin life along the world's coastlines. The broader implications of this anomaly extend beyond the boundaries of the ocean to encompass global environmental stability. By accelerating decomposition, regulating disease, and influencing nutrient cycles, crabs contribute to the productivity of ecosystems that generate oxygen, sequester carbon, and sustain fisheries essential to human survival. Their opportunistic feeding strategies, intensified by hunger and environmental stress, reinforce the interconnectedness of marine and terrestrial systems, illustrating how the smallest actors can exert profound influence over planetary processes. The battlefield of chance upon which they operate becomes a crucible of ecological transformation, where survival depends upon adaptability and resilience. The final image unfolds along a moonlit shoreline, where the tide retreats to reveal a mosaic of sand, coral fragments, and drifting seaweed. From beneath the sediment, crabs emerge in silent procession, their armored bodies glinting under the pale light as they converge upon the remnants of a fallen fish. Claws rise and fall with deliberate precision, dismantling the carcass and returning its essence to the sea. Around them, the ecosystem responds. Nutrients disperse, microorganisms flourish, and life renews itself in the wake of decay. In this quiet convergence of hunger and opportunity, the anomaly reveals its truth with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Entire marine ecosystems have shifted in response to the tireless journeys of a bird that cannot fly, yet traverses oceans with astonishing endurance. Across the southern hemisphere, penguins have shaped the dynamics of marine food webs, transporting nutrients from the sea to the land and influencing the productivity of coastal ecosystems and polar climates. Their migrations redistribute energy across vast distances, linking remote feeding grounds with breeding colonies that fertilize barren landscapes through guano deposits rich in nitrogen and phosphorus. These nutrient transfers stimulate microbial activity, enrich terrestrial vegetation, and influence carbon cycling in some of the most extreme environments on Earth. When prey becomes scarce, penguins extend their hunting expeditions farther into the open ocean, transforming their daily struggle for survival into a force that reverberates through climate systems, fisheries, and global ecological networks. The anomaly of the penguin lies not merely in its endurance, but in the way hunger compels it to push beyond its physical limits, reshaping ecosystems through relentless pursuit beneath the waves. The biological machinery that enables these extraordinary journeys reflects a remarkable evolutionary transformation from flight to aquatic mastery. Penguins possess dense, streamlined bodies optimized for hydrodynamic efficiency, their wings reshaped into rigid flippers that generate powerful thrust through water. Their bones are solid rather than hollow, reducing buoyancy and allowing precise control during deep dives. A thick layer of blubber insulates against freezing temperatures, while densely packed feathers trap air and create a waterproof barrier that maintains body heat. Beneath this insulating armor lies a sophisticated circulatory system adapted for prolonged submersion, including a high concentration of myoglobin in muscle tissues that stores oxygen and supports sustained underwater activity. Penguins regulate their heart rate and redirect blood flow during dives, conserving oxygen for vital organs while minimizing metabolic expenditure. These adaptations allow them to descend to remarkable depths and remain submerged for extended periods, pursuing prey with efficiency in some of the coldest and most unforgiving waters on the planet. Under stable conditions, penguins exploit predictable concentrations of fish, krill, and squid, coordinating their foraging trips with seasonal productivity and ocean currents. Yet, environmental variability and shifting prey distributions disrupt these patterns, forcing penguins to travel farther and dive deeper in search of sustenance. Hunger transforms routine hunting into an arduous ordeal, compelling individuals to extend their journeys across increasingly distant feeding grounds. Each dive demands precise control of oxygen reserves, muscular endurance, and thermoregulation, while repeated submersion imposes physiological strain that accumulates over time. Failure to capture sufficient prey can lead to rapid energy depletion, jeopardizing not only the survival of individual birds, but also the stability of breeding colonies dependent upon their return. In these moments of scarcity, every dive becomes a high-stakes decision, a delicate balance between nourishment and exhaustion in an environment where the margin for error is perilously narrow. The ecological consequences of these extended hunting expeditions ripple outward through marine ecosystems with profound intensity. As penguins expand their foraging ranges, they exert predation pressure on prey populations across vast swaths of the Southern Ocean, influencing the distribution of krill, fish, and squid that form the foundation of polar food webs. These shifts reverberate through the ecosystem, affecting the abundance of seals, whales, and seabirds that compete for the same resources. In regions where penguins intensify their hunting efforts due to prey scarcity, localized depletion of krill can alter phytoplankton dynamics and nutrient cycling, reshaping the productivity of the Southern Ocean and influencing global carbon sequestration. Each extended foraging trip thus becomes a biological thread woven into the fabric of planetary climate regulation, linking the survival of a single bird to the stability of Earth's environmental systems. A surprising escalation emerges as penguins act as vectors of nutrient transport, redistributing marine-derived resources to terrestrial ecosystems through their breeding colonies. The guano deposited by millions of birds fertilizes coastal soils, stimulating the growth of algae, mosses, and microorganisms that support complex terrestrial food webs in otherwise barren polar landscapes. This nutrient enrichment enhances carbon storage in Antarctic ecosystems, reinforcing their role as climate regulators and contributing to the stability of global atmospheric processes. When hunger forces penguins to travel farther and remain underwater longer, the success or failure of their hunts determines the flow of nutrients from ocean to land, shaping the productivity and resilience of ecosystems that extend far beyond the icy margins of their habitat. The cascading effects of penguin foraging behavior extend into coastal and marine environments that influence global fisheries and biodiversity. By regulating populations of fish and krill, penguins contribute to the balance of marine food webs that sustain commercially valuable species and support human livelihoods. Their presence reflects the health of the Southern Ocean, serving as a biological indicator of ecosystem stability and environmental change. When penguins must travel farther to find food, their altered foraging patterns signal shifts in ocean productivity that reverberate through fisheries, economies, and global food security. The endurance-driven journeys of these flightless birds thus intersect with human survival, illustrating the profound interconnectedness of marine ecosystems and human societies. Human civilization has long been entwined with the fate of penguins, whose reliance on krill and fish mirrors the demands of global fisheries. The Southern Ocean supports lucrative industries that harvest these same resources, creating competition between human enterprise and wildlife for limited food supplies. As climate change alters ocean temperatures and sea ice dynamics, prey distributions shift, compelling penguins to extend their hunting trips and intensify their dives. These changes reflect broader environmental transformations that influence fisheries, global markets, and the stability of food systems upon which millions depend. The endurance of penguins, stretched by hunger and environmental pressure, becomes a silent indicator of planetary change, revealing the vulnerability of ecosystems upon which human prosperity relies. Beyond their ecological and economic significance, penguins have contributed to scientific understanding of physiology, climate change, and marine ecology. Research into their diving adaptations has informed studies of hypoxia tolerance, thermoregulation, and cardiovascular function, advancing knowledge in fields ranging from medicine to environmental science. Satellite tracking of penguin migrations has revealed the shifting boundaries of ocean productivity, providing critical insights into climate-driven changes in marine ecosystems. These discoveries underscore the intricate relationship between biological adaptation and human understanding, illustrating how the survival strategies of penguins illuminate the hidden dynamics of the Southern Ocean and the broader Earth system. An unexpected twist reframes the narrative of resilience and endurance. Despite their extraordinary adaptations, penguins are acutely vulnerable to environmental disruption, particularly the loss of sea ice and the depletion of krill populations driven by climate change and industrial exploitation. As sea ice retreats and ocean temperatures rise, the distribution of prey shifts farther from breeding colonies, forcing penguins to undertake increasingly arduous journeys that stretch their physiological limits. Extended hunting trips elevate the risk of exhaustion, predation, and reproductive failure, threatening the stability of populations that have endured for millennia. The very endurance that defines the penguin's anomaly becomes a liability in a rapidly changing world, revealing a fragile equilibrium between adaptation and survival. This vulnerability introduces new tension into the ecological narrative, as the decline of penguin populations could destabilize marine food webs and disrupt nutrient cycles that sustain polar ecosystems and influence global climate regulation. Without the regulating presence of these predators, Prey populations may expand or collapse unpredictably, altering the productivity of the Southern Ocean and diminishing its capacity to absorb atmospheric carbon dioxide. The disappearance of penguins would not merely signify the loss of a charismatic species, but would represent a profound disruption of ecological processes that link ocean, land, and atmosphere. Their struggle to endure in the face of environmental change thus reflects a broader planetary challenge, underscoring the delicate balance upon which life depends. As hunger stretches their physical limits and environmental pressures intensify, penguins continue to embark upon extended hunting journeys that test the boundaries of endurance. Each dive into the icy depths demands precise management of oxygen reserves and energy expenditure, while each return to the colony represents a triumph of survival against the relentless forces of nature. In this silent drama of persistence, the penguin embodies the tension between resilience and vulnerability, revealing how necessity drives adaptation in one of the most extreme environments on Earth. Their journeys, dictated by hunger and sustained by evolutionary ingenuity, resonate across ecosystems and climate systems alike. The final image unfolds along a windswept Antarctic coastline beneath a pale, luminous sky. A solitary penguin stands at the water's edge, its dark silhouette poised against the endless expanse of the Southern Ocean. With a sudden leap, it plunges into the frigid depths, wings beating with relentless precision as it descends in pursuit of distant prey. Beneath the surface, currents swirl and life converges, while above, the colony waits in silent anticipation. Each dive carries the weight of survival. Each return sustains the fragile balance of an ecosystem bound to the rhythms of the sea. In this enduring cycle of hunger and perseverance, the anomaly reveals its truth with unmistakable clarity. The ocean does not merely exist. It acts. It reshapes the world. Across the vast expanse of the world's oceans, the relentless pursuit of survival by squid has quietly influenced the balance of marine ecosystems and the stability of global food webs. These elusive predators, propelled by bursts of astonishing speed, have shaped the dynamics of open ocean hunting grounds for millions of years, redistributing energy through the pelagic realm and sustaining some of the planet's most iconic marine giants. From deep-sea whales to migratory seabirds, entire species depend upon squid as a primary source of nourishment, linking abyssal darkness to surface waters and binding the biological machinery of the oceans into a single, interconnected system. When hunger intensifies and prey becomes scarce, squid are forced into a desperate rhythm of repeated high-speed attacks, a biological gamble that drains their energy reserves with unforgiving efficiency. In this silent contest between speed and survival, the fate of a single predator reverberates across ecosystems and influences the balance of life on a planetary scale. The biological mechanism behind this extraordinary lifestyle reveals one of evolution's most refined engines of motion. Squid propel themselves through jet propulsion, drawing water into their mantle cavity and forcefully expelling it through a narrow siphon to generate rapid acceleration. This system, powered by powerful mantle muscles and supported by a highly efficient circulatory network, allows squid to achieve explosive bursts of speed that rival the fastest swimmers in the ocean. Unlike fish that rely on continuous propulsion, squid expend enormous energy in short, intense movements, sacrificing efficiency for velocity. Their muscular mantle contains a high density of mitochondria, enabling rapid energy conversion, but also demanding a constant supply of oxygen and nutrients. A sophisticated closed circulatory system, rare among invertebrates, delivers oxygen with remarkable efficiency through the use of copper-based hemocyanin, while their large gills facilitate rapid gas exchange. Yet this metabolic intensity comes at a cost, as the very mechanism that grants them their speed also accelerates exhaustion when hunts fail. Hunger transforms these bursts of propulsion into a relentless cycle of risk. In periods of prey scarcity, squid must attack repeatedly, each failed strike consuming valuable energy reserves and pushing their physiology toward collapse. Their nervous system, among the most advanced of any invertebrate, coordinates precise movements with extraordinary speed, allowing them to track prey using highly developed eyes, comparable in complexity to those of vertebrates. Chromatophores embedded within their skin enable rapid color changes that aid in camouflage and communication, while bioluminescent organs in some species provide stealth in the darkness of the deep sea. These adaptations enhance hunting success, yet they cannot offset the fundamental limitation imposed by jet propulsion. Speed is metabolically expensive. With each unsuccessful pursuit, the squid's energy stores diminish, and the margin between survival and starvation narrows. This precarious balance triggers cascading effects throughout marine ecosystems. As squid intensify their hunting efforts during periods of hunger, they exert increased predation pressure on fish, crustaceans, and smaller cephalopods, reshaping the structure of pelagic food webs. Fluctuations in squid populations can influence the abundance of commercially important fish species, altering recruitment patterns and shifting the dynamics of fisheries across entire ocean basins. In regions where squid thrive, they serve as a vital intermediary, transferring energy from plankton-rich waters to apex predators such as sperm whales, sharks, and tuna. When their numbers decline due to energetic stress or environmental change, these predators must adapt by altering their migration routes and feeding strategies, creating ripple effects that extend from the abyss to coastal ecosystems. A surprising escalation emerges from the role squid play in biogeochemical cycling. Through their daily vertical migrations, many species ascend from the depths to feed in nutrient-rich surface waters before descending once more into the darkness. This movement transports organic carbon and nutrients through the water column, contributing to the ocean's biological pump and influencing the sequestration of carbon dioxide from the atmosphere. When hunger forces squid to extend their hunting efforts, these migrations intensify, accelerating the transfer of carbon to deeper waters and reinforcing the ocean's capacity to regulate global climate. Thus, the repeated bursts of speed that define the squid's survival strategy also participate in one of the planet's most critical climate-regulating processes. The cascade continues across coastal ecosystems and fisheries, where squid serve as both predator and prey in complex trophic networks. Their abundance supports seabirds, marine mammals, and large predatory fish that sustain human livelihoods and global markets. In regions such as the Pacific and Atlantic Oceans, squid fisheries have become among the most economically significant in the world, supplying millions of tons of seafood annually. These fisheries depend upon the stability of squid populations, which in turn are shaped by environmental conditions and the energetic constraints of their hunting behavior. When repeated failed hunts weaken squid populations, fluctuations in their abundance reverberate through fisheries and economies, illustrating the profound connection between the metabolic struggles of a single species and the prosperity of human societies. Human civilization has long been intertwined with the fate of squid, whose presence influences food security, cultural traditions, and scientific discovery. From ancient maritime cultures that relied on squid as a staple food to modern global markets that distribute cephalopod products across continents, these animals occupy a central role in human economies. Their rapid growth rates and sensitivity to environmental change make them valuable indicators of ocean health, providing insights into the effects of climate variability and shifting marine ecosystems. Scientific research into squid physiology has advanced understanding of neural function, camouflage, and biomechanics, inspiring innovations in robotics, materials science, and medical technology. The trade-off between energy and survival that governs their existence thus resonates beyond the ocean, shaping human knowledge and influencing the development of technologies inspired by the natural world. Yet an unexpected twist emerges from this narrative of resilience and ecological significance. Despite their adaptability and extraordinary speed, squid are inherently fragile, their survival constrained by the relentless demands of their metabolism. Unlike many long-lived marine predators, most squid species possess short lifespans, growing rapidly and reproducing only once before dying. This life history strategy leaves them acutely vulnerable to environmental fluctuations, including changes in ocean temperature, oxygen levels, and prey availability. When hunger forces them into repeated high-speed pursuits, their energy reserves diminish rapidly, and exhaustion can lead to sudden mortality. The very speed that defines their anomaly becomes an unsustainable burden, transforming their greatest strength into a liability in a changing ocean. This fragility introduces new tension into the ecological web. As climate change alters ocean temperatures and productivity, the distribution of squid prey shifts, forcing them to expend even greater energy in pursuit of sustenance. In oxygen-depleted zones expanding across the world's oceans, the metabolic demands of jet propulsion become increasingly difficult to sustain, pushing squid populations toward physiological limits. These changes reverberate through food webs, affecting predators that rely upon squid and destabilizing fisheries that support human communities. The decline of squid populations would disrupt the transfer of energy across marine ecosystems and diminish the ocean's capacity to regulate climate, illustrating the delicate balance between adaptation and vulnerability in an era of environmental transformation. A further ecological escalation reveals the paradox of their success. In some regions, warming oceans have led to population booms among certain squid species, enabling them to outcompete fish and alter marine food webs. These expansions demonstrate their remarkable adaptability, yet they also highlight the instability of ecosystems undergoing rapid change. Where squid populations surge, they can reshape trophic dynamics, influencing the distribution of predators and prey while altering nutrient cycles within the ocean. This duality underscores the anomaly of the squid, an organism capable of both sustaining ecosystems and destabilizing them, depending on the shifting conditions of the marine environment. As hunger continues to drive their relentless pursuit of prey, squid embody the tension between speed and survival, navigating a world where efficiency is sacrificed for urgency. Each burst of propulsion represents a calculated risk, a momentary triumph of velocity that carries the price of metabolic exhaustion. Their lives unfold in a delicate balance of energy and necessity, where repeated failed hunts can drain their reserves and force them toward the brink of collapse. In this silent struggle, the ocean becomes a theater of endurance, where survival depends upon the capacity to outrun hunger while confronting the limits of physiology. The closing image emerges in the dim twilight of the open ocean, where a solitary squid hovers in the water column, its body pulsing with faint bioluminescent light. Below, darkness stretches into the abyss, while above, distant prey glimmer like scattered stars. With a sudden contraction of its mantle, the squid launches forward in a burst of speed, its form slicing through the water in a desperate pursuit. Each surge of motion draws upon dwindling reserves. Each failure intensifies the urgency of the hunt. Around it, currents carry nutrients. Predators circle in silence, and the fragile balance of the ocean shifts with every fleeting decision. In this relentless contest between energy and survival, the anomaly reveals its truth with unyielding clarity. The ocean does not simply exist, it acts. It reshapes the world. Across the warm tropical seas of the Indo-Pacific, a silent hunter has reshaped coastal ecosystems and influenced the balance of life in waters that sustain millions of people. Sea snakes, descendants of terrestrial reptiles that returned to the ocean tens of millions of years ago, have altered marine food webs by exerting predation pressure on fish populations that shape coral reef dynamics and coastal productivity. Their presence influences the distribution of prey species, stabilizes ecological hierarchies, and contributes to the health of reef systems that protect shorelines and support fisheries vital to human survival. Yet, beneath this ecological influence lies a biological paradox. These reptiles must breathe air. Each hunt beneath the waves becomes a race against oxygen depletion, and when hunger intensifies, sea snakes are forced into longer dives and riskier ascents, transforming survival into a perilous negotiation between time, breath, and predation. In this delicate balance, the actions of a single hunter ripple across ecosystems, shaping environments that sustain life far beyond the horizon. The biological mechanism that governs this extraordinary existence reveals one of evolution's most remarkable adaptations. Sea snakes possess elongated, laterally compressed bodies that enable efficient undulatory swimming through complex reef structures and open water. Their scales are reduced and smooth, minimizing drag and allowing seamless movement through dense coral labyrinths and turbulent currents. A paddle-shaped tail acts as a powerful rudder, providing thrust and maneuverability during pursuit. Beneath their streamlined exterior lies a highly specialized respiratory system. Unlike fish, sea snakes rely on lungs for oxygen intake, and many species possess a single elongated lung that extends nearly the entire length of the body, functioning not only as a respiratory organ, but also as a buoyancy regulator. This adaptation allows them to control their depth with precision, conserving energy during prolonged dives. Their physiology extends further into the realm of biochemical innovation. Sea snakes exhibit an exceptional capacity for cutaneous respiration, absorbing a portion of their oxygen directly through the skin. This adaptation allows them to remain submerged longer than most air-breathing reptiles, reducing the frequency of surfacing and minimizing exposure to predators. Their blood contains hemoglobin with a high affinity for oxygen, enabling efficient storage and transport even in low oxygen conditions. Muscles rich in myoglobin act as reservoirs, sustaining metabolic activity during extended dives. Yet despite these adaptations, the fundamental constraint remains unchanged. Sea snakes must return to the surface to breathe. Every descent beneath the waves carries an invisible timer, and hunger transforms this physiological limitation into a dangerous gamble. When prey becomes scarce, sea snakes are compelled to extend their hunting efforts, diving deeper and remaining submerged longer in pursuit of elusive fish and eels. Each prolonged dive increases the risk of oxygen depletion, forcing the snake to ration its energy while navigating the intricate terrain of coral reefs and seagrass meadows. Failure to capture prey intensifies the urgency of survival, driving repeated descents that strain physiological limits. As oxygen reserves diminish, metabolic processes slow, and lactic acid accumulates within muscle tissues, creating a silent countdown toward exhaustion. Hunger transforms hunting into a high-stakes endeavor, where every moment beneath the surface must be calculated with precision, and each ascent to breathe exposes the snake to predators waiting in the open water above. This tension between survival and suffocation triggers cascading effects throughout marine ecosystems. As sea snakes extend their foraging ranges during periods of scarcity, they alter the distribution and behavior of prey species across reef systems and coastal habitats. Their predation regulates populations of fish that graze on algae, influencing the balance between coral growth and algal overgrowth that determines the health of reef ecosystems. In regions where sea snakes intensify their hunting efforts, shifts in prey abundance can reshape community structures, affecting the resilience of coral reefs that buffer coastlines from storms and erosion. These ecological adjustments ripple outward, linking the survival of a single predator to the stability of habitats that protect human settlements and support biodiversity. A surprising escalation emerges from the role sea snakes play in connecting ecosystems through nutrient cycling. As they hunt across seagrass beds, mangroves and coral reefs, they transport energy between distinct marine environments, redistributing nutrients through predation and excretion. This movement contributes to the productivity of coastal ecosystems that sustain fisheries and support carbon sequestration in blue carbon habitats. When hunger forces sea snakes to travel farther and dive longer, their ecological footprint expands, influencing nutrient flows across habitats that store vast quantities of carbon and mitigate the effects of climate change. The rhythm of their breathing, dictated by the need for oxygen, becomes intertwined with the broader dynamics of planetary climate regulation. The cascade extends into pelagic ecosystems where sea snakes must surface to breathe, exposing themselves to aerial and aquatic predators. Birds of prey, sharks and large fish patrol the surface, exploiting moments of vulnerability as snakes emerge for air. During periods of starvation, extended dives delay surfacing, pushing snakes to the brink of hypoxia and increasing the likelihood of fatal miscalculations. This interplay between predator and prey shapes behavioral adaptations across multiple trophic levels, influencing hunting strategies, migration patterns, and energy flows throughout the marine environment. Each ascent for breath becomes a moment of heightened risk, a convergence of necessity and danger that reverberates through the food web. Human civilization has long been entwined with the presence of sea snakes, whose influence extends from coastal fisheries to global biomedical research. In many regions of Southeast Asia and the Indo-Pacific, sea snakes play a role in sustaining fish populations that support local economies and food security. Their predation helps maintain ecological balance within reef systems that underpin commercial fisheries and tourism industries. Moreover, the potent venom of sea snakes, among the most toxic in the natural world, has inspired advances in medical science, contributing to research in neurology, pain management, and anti-venom development. These biological compounds, refined through millions of years of evolution, hold potential for therapeutic innovation, illustrating how the survival strategies of marine reptiles intersect with human health and technological progress. A further ecological escalation arises from the sensitivity of sea snakes to environmental change. As ocean temperatures rise and coastal habitats degrade, shifts in prey availability compel these reptiles to extend their hunting efforts and remain submerged longer, intensifying the risks associated with oxygen depletion. Pollution, habitat destruction, and bycatch in fishing operations threaten populations already constrained by their physiological dependence on atmospheric oxygen. In regions where sea snakes decline, imbalances in prey populations can lead to cascading ecological consequences, altering reef dynamics and diminishing the resilience of coastal ecosystems. The struggle of these reptiles to balance hunger with the need to breathe reflects broader environmental pressures that influence the stability of marine systems upon which human societies depend. An unexpected twist reframes the narrative of resilience and adaptation. Despite their formidable venom and remarkable physiological innovations, sea snakes are among the most fragile of marine predators, their survival intricately tied to precise environmental conditions. Unlike many marine animals that extract oxygen directly from water, sea snakes remain tethered to the surface, bound by the necessity of breath in a world dominated by water. This reliance creates a paradox of vulnerability, as their greatest adaptations cannot free them from the fundamental constraint of air. As climate change alters ocean productivity and prey distributions, the increasing need for prolonged dives places them at greater risk of hypoxia and predation. The very strategy that sustains their survival becomes a perilous liability in a rapidly changing ocean. This vulnerability introduces new tension into the ecological narrative, as the decline of sea snake populations could destabilize marine food webs and disrupt the delicate balance of coastal ecosystems. Without their regulating presence, prey species may proliferate unchecked, altering the composition of reef communities and accelerating the degradation of habitats that protect shorelines and sustain fisheries. The disappearance of sea snakes would not merely signify the loss of a unique lineage of reptiles, but would represent a disruption of ecological processes that link biodiversity, climate regulation, and human survival. Their silent struggle to endure beneath the waves reflects the broader fragility of life in a changing world, where adaptation and vulnerability coexist in delicate equilibrium. As hunger continues to drive their relentless pursuit of prey, sea snakes navigate a world defined by risk and precision. Each descent into the depths is governed by an invisible countdown, a race against oxygen depletion that demands perfect timing and unwavering efficiency. Their sinuous bodies glide through coral labyrinths and shadowed seagrass meadows, propelled by instinct and sustained by the promise of sustenance. Yet every prolonged dive tightens the margin between survival and suffocation, while each ascent to breathe exposes them to predators waiting at the surface. In this perpetual cycle of descent and emergence, necessity dictates movement, and survival hinges upon the delicate balance between breath and hunger. The closing image unfolds in the amber glow of a tropical sunset, where tranquil waters conceal the intricate drama of life beneath the surface. A solitary sea snake ascends from the depths, its slender body undulating with measured grace as it approaches the shimmering boundary between ocean and sky. For a fleeting moment it breaks the surface to draw a breath, the air rippling across scales adapted for a world of water, yet bound to the atmosphere above. Below, the reef pulses with life. Currents carry nutrients across vast distances, and predators circle in silent anticipation. With a final inhalation, the snake descends once more into the blue expanse, vanishing into a realm where survival is dictated by timing, endurance, and the unyielding rhythm of oxygen and hunger. In this silent choreography of risk and resilience, the anomaly reveals its truth with undeniable clarity. The ocean does not simply exist. It acts. It reshapes the world. The fate of entire coastlines has, at times, hinged on the survival of a small marine mammal whose labor determines whether underwater forests flourish or collapse. When sea otters vanish, kelp forests unravel, shorelines lose natural protection, and marine biodiversity fractures into impoverished remnants. Across the northern Pacific, the rise and fall of this unassuming predator has rewritten ecological history, reshaping fisheries, altering carbon storage, and influencing the stability of coastal communities. The sea otter is not merely a resident of the ocean's margins. It is an architect of balance, a biological anomaly whose survival depends on relentless effort. Its existence reveals a stark truth. In the ocean's cold shallows, survival is not effortless grace, but unending labor. This labor begins with anatomy exquisitely tuned to a life of perpetual expenditure. Unlike whales and seals, sea otters lack insulating blubber, relying instead on the densest fur in the animal kingdom to trap air and preserve warmth. Each strand of fur creates a microscopic barrier against frigid waters, but maintaining this insulation requires constant grooming and an extraordinarily high metabolic rate. To fuel this internal furnace, sea otters must consume vast quantities of food each day, often devouring a significant portion of their own body mass. Their forelimbs, remarkably dexterous, function with almost primate-like precision, capable of manipulating objects, probing crevices, and wielding tools. Within the loose folds of skin beneath their forearms, they carry stones gathered from the seabed, each chosen for its size and shape. These rocks are not ornaments, but instruments of survival, essential tools that transform brute strength into strategic efficiency. When preferred prey becomes scarce, the otter's reliance on these tools intensifies. Clams, mussels, sea urchins, and crabs form the foundation of their diet, but fluctuations in prey populations force them to adapt. As easy meals disappear, sea otters turn to harder-shelled and more elusive organisms, increasing the complexity and duration of each feeding attempt. They float on their backs, balancing stones upon their chests as improvised anvils, striking shellfish with rhythmic precision until the armor yields. This behavior, rare among marine mammals, reveals a profound evolutionary adaptation. Intelligence fused with necessity. The otter's survival hinges on its capacity to transform the inert geology of the seabed into an extension of its own anatomy, converting rocks into instruments that unlock nourishment from otherwise inaccessible prey. This relentless foraging sets in motion a cascade of ecological consequences that ripple far beyond the otter's immediate environment. By consuming sea urchins, sea otters regulate populations of these voracious grazers, preventing them from stripping kelp forests down to barren rock. In regions where otters thrive, lush kelp canopies rise from the seafloor, forming dense underwater forests that nurture fish, invertebrates, and countless other marine organisms. These kelp forests serve as nurseries for commercially valuable species, stabilizing ecosystems that sustain fisheries and coastal economies. When otters decline, however, urchins proliferate unchecked, devouring kelp at an alarming rate, and transforming vibrant habitats into desolate expanses known as urchin barrens. The disappearance of a single predator thus triggers a profound ecological transformation, unraveling complex food webs and reshaping the productivity of entire coastal regions. The consequences extend beyond biodiversity into the realm of climate regulation. Kelp forests act as powerful carbon sinks, absorbing atmospheric carbon dioxide and storing it within their tissues and surrounding sediments. By safeguarding these forests, sea otters indirectly contribute to the mitigation of climate change, reinforcing the stability of coastal ecosystems in an era of environmental uncertainty. Each shell cracked open by an otter reverberates through this intricate network, preserving habitats that capture carbon, dampen wave energy, and protect shorelines from erosion. In this way, the otter's labor becomes a silent form of environmental stewardship, anchoring fragile ecosystems against the accelerating pressures of a warming planet. As prey declines and hunger intensifies, the demands of survival grow increasingly arduous. Sea otters must expand their dietary range, targeting tougher, more resilient prey that require greater effort to exploit. The use of tools becomes more frequent and more deliberate, each feeding event transforming into a prolonged struggle between predator and armor. This escalation forces otters into deeper and more exposed waters, where currents are stronger and predators more numerous. Their relentless pursuit of nourishment exposes them to risks from sharks, environmental hazards, and human activity, illustrating the delicate balance between energy gained and energy expended. Survival becomes a calculation measured in calories and endurance, where the margin between sustenance and starvation narrows with every passing tide. These ecological dynamics intersect profoundly with human civilization. Coastal fisheries depend upon the stability of kelp forests nurtured by sea otters, as these underwater ecosystems provide shelter and breeding grounds for species essential to commercial harvests. The presence of sea otters has been linked to increased biodiversity and productivity in nearshore environments, supporting livelihoods and sustaining cultural traditions in coastal communities. At the same time, their consumption of shellfish has sparked conflicts with fisheries that rely on similar resources, revealing the complex interplay between conservation and economic interests. The otter's labor-intensive survival thus becomes a point of convergence between ecological resilience and human ambition, highlighting the intricate connections that bind humanity to the health of marine ecosystems. Beyond fisheries, the influence of sea otters extends to shoreline protection and global markets. Kelp forests dampen the force of waves, reducing coastal erosion and safeguarding infrastructure from storm surges. By maintaining these natural barriers, sea otters indirectly shield coastal settlements from the destructive power of the ocean. This ecological service carries economic value, mitigating the need for costly artificial defenses and preserving the integrity of coastal habitats. The disappearance of sea otters, conversely, amplifies the vulnerability of shorelines, exposing communities to the relentless advance of waves and rising seas. In this context, the otter's tireless labor becomes an unseen ally in the defense of human civilization, reinforcing the fragile boundary between land and ocean. A new and unexpected dimension emerges from this narrative of industrious survival. Despite their ecological significance and remarkable adaptability, sea otters remain profoundly fragile. Their dependence on dense fur renders them vulnerable to oil spills, which strip away the insulating air layer and expose them to lethal hypothermia. Pollution, habitat degradation, and fluctuations in prey availability further threaten their survival, underscoring the precariousness of their existence. Ironically, the very traits that make sea otters indispensable architects of marine ecosystems also render them susceptible to environmental disruption. Their survival hinges not only on their own labor, but on the integrity of the oceanic systems they sustain. This fragility reframes the sea otter's role as a keystone species whose decline could destabilize entire coastal regions. The loss of sea otters unleashes cascading effects that reverberate through kelp forests, fisheries, and carbon cycles, undermining ecological resilience and economic stability. Their absence transforms thriving ecosystems into impoverished seascapes, diminishing biodiversity and eroding the natural defenses that protect coastlines. In this context, the otter emerges not merely as a survivor, but as a sentinel of ecological balance, its fate intertwined with the health of the oceans and the future of human communities. The deeper anomaly lies in the relationship between labor and survival. Unlike apex predators that rely on speed or strength, the sea otter endures through relentless effort, transforming stones into tools and hunger into innovation. Each dive, each strike of rock against shell, represents a negotiation between energy and existence, a testament to the delicate equilibrium that governs life in the ocean's margins. This labor-intensive survival reveals a profound evolutionary truth. Adaptability, rather than dominance, often determines resilience in an ever-changing world. As climate change reshapes marine ecosystems and prey distributions shift, the demands placed upon sea otters intensify. Rising ocean temperatures, ocean acidification, and human exploitation alter the availability of shellfish, forcing otters to expand their foraging ranges and expend greater energy in search of nourishment. The balance between caloric intake and metabolic demand grows increasingly precarious, illustrating the fragile calculus upon which their survival depends. Each stone lifted from the seafloor becomes a symbol of perseverance, an instrument wielded in the quiet struggle against environmental uncertainty. The final image unfolds along a mist-shrouded coastline where kelp forests sway beneath the surface like submerged cathedrals. A solitary sea otter drifts upon the tide, a stone balanced upon its chest, its movements deliberate and unhurried. With each measured strike, a shell yields, releasing sustenance that sustains not only the otter, but the intricate web of life surrounding it. Beneath the waves, forests endure, carbon is captured, and shorelines remain intact, their stability forged by the tireless labor of a single predator. In this silent act of survival, the anomaly reveals itself with undeniable clarity. The ocean does not merely exist. It acts. It reshapes the world. The balance of life in the world's cold oceans has been shaped by a predator that moves between safety and danger with calculated precision, altering marine ecosystems and influencing the survival of species across vast hemispheres. Seals, driven by hunger and bound to the rhythms of ice and sea, have reshaped predator-prey dynamics from polar waters to temperate coastlines, redistributing energy through food webs that sustain whales, sharks, seabirds, and human fisheries alike. Their foraging journeys link nutrient-rich feeding grounds with breeding colonies on remote shores, transferring marine-derived nutrients onto land and influencing coastal productivity. When prey becomes scarce, seals are forced into perilous hunting grounds patrolled by apex predators, venturing into zones where survival depends on a delicate balance between starvation and predation. In this silent struggle, their movements ripple through ecosystems, altering the distribution of marine life and revealing how hunger compels life to confront risk on a planetary scale. The biological machinery that enables seals to navigate this dangerous existence reflects an evolutionary masterpiece of adaptation to aquatic life. Streamlined bodies taper into powerful hind flippers, allowing efficient propulsion through water while minimizing drag, and thick layers of blubber provide insulation against freezing temperatures while serving as an essential reservoir of energy during prolonged fasting. Beneath this insulating armor lies a sophisticated circulatory system optimized for deep diving and extended submersion, including elevated concentrations of hemoglobin and myoglobin that store oxygen and support sustained underwater activity. During dives, seals exhibit remarkable physiological control, slowing their heart rates and redirecting blood flow to vital organs while tolerating elevated levels of carbon dioxide. Their lungs collapse under pressure, reducing nitrogen absorption and protecting against decompression stress, allowing them to descend into the depths with extraordinary resilience. These adaptations enable seals to hunt efficiently in the ocean's most unforgiving environments, yet they also impose strict energetic demands that intensify when prey becomes scarce. When hunger tightens its grip, seals must expand their foraging range, venturing beyond familiar feeding grounds into waters inhabited by formidable predators. Under stable conditions, they exploit predictable concentrations of fish, squid, and crustaceans, synchronizing their movements with seasonal productivity and ocean currents. Environmental variability, shifting prey distributions, and declining ice coverage disrupt these patterns, forcing seals to hunt longer and dive deeper in search of sustenance. Each journey into predator-rich waters represents a calculated risk, as encounters with orcas and large sharks become more likely in regions where prey congregates. The need to feed drives seals into these perilous zones, transforming routine foraging into a high-stakes gamble where survival hinges on vigilance, speed, and endurance. The ecological consequences of this risk-driven behavior reverberate through marine food webs with profound intensity. As seals intensify their hunting efforts in predator-dense regions, they exert increased pressure on fish and squid populations, influencing the distribution and abundance of prey species across entire ocean basins. These shifts cascade through ecosystems, affecting seabirds, whales, and predatory fish that rely upon the same resources. In regions where seals must venture farther to find food, their movements redistribute predation pressure and alter the spatial dynamics of marine communities. Each incursion into dangerous waters becomes an ecological event, reshaping the balance of life beneath the waves and influencing the stability of ecosystems that regulate global climate and biodiversity. A surprising escalation emerges from the role seals play in nutrient transport and coastal productivity. By feeding in offshore waters and returning to haul-out sites along coastlines and ice flows, seals transfer marine-derived nutrients to terrestrial and nearshore environments through excretion and carcass deposition. These nutrient inputs enrich coastal ecosystems, stimulating the growth of algae and supporting microbial communities that form the foundation of local food webs. In polar regions, seal colonies fertilize nutrient-poor landscapes, influencing the productivity of mosses and lichens and supporting invertebrate populations that sustain seabirds and other wildlife. When hunger forces seals into riskier hunting grounds, the success or failure of their foraging expeditions determines the flow of nutrients across ecosystems, shaping the resilience of habitats that extend from the open ocean to the frozen margins of the poles. The cascade continues across climate systems and fisheries, where seals serve as both predators and prey within intricate trophic networks. Their consumption of fish and squid regulates populations that sustain commercial fisheries, influencing recruitment patterns and market stability across coastal economies. In regions where seals intensify their foraging due to prey scarcity, their predation can alter the abundance of commercially valuable species, creating ripple effects that extend into global seafood markets. At the same time, seals themselves provide nourishment for apex predators such as orcas and large sharks, linking lower trophic levels to the highest tiers of the marine food web. Their presence reflects the health of ocean ecosystems, serving as a biological indicator of environmental change and revealing shifts in productivity that resonate across industries and continents. Human civilization has long been entwined with the fate of seals, whose ecological roles intersect with cultural traditions, economic systems, and scientific discovery. Indigenous communities have relied upon seals for food, clothing, and tools for millennia, shaping cultural identities and survival strategies in some of the harshest environments on Earth. In modern times, seals influence fisheries management, marine conservation efforts, and global markets, reflecting the intricate relationship between human societies and marine ecosystems. Scientific research into seal physiology has advanced understanding of hypoxia tolerance, cardiovascular adaptation, and thermoregulation, informing medical and environmental studies that extend far beyond the ocean. The risk-laden journeys of seals, driven by hunger and necessity, thus resonate through human history and illuminate the interconnectedness of biological adaptation and societal development. A further ecological escalation reveals the impact of climate change on the delicate balance between starvation and predation. As warming temperatures alter ocean currents and reduce sea ice coverage, the distribution of prey shifts farther from traditional feeding grounds, compelling seals to travel greater distances and hunt in increasingly dangerous waters. These changes intensify their exposure to predators and elevate the energetic costs of foraging, threatening the stability of populations that depend upon predictable seasonal cycles. In polar regions, the loss of ice platforms reduces safe resting sites and breeding habitats, forcing seals into open water where vulnerability to predation increases. The consequences of these shifts reverberate through ecosystems, affecting predator-prey dynamics, nutrient cycles, and the productivity of marine environments that regulate global climate. An unexpected twist reframes the narrative of resilience and adaptation. Despite their formidable physiology and ecological significance, seals are acutely vulnerable to environmental disruption and human activity. Pollution, entanglement in fishing gear, and habitat degradation threaten their survival, while climate-driven changes in prey availability force them into increasingly perilous hunting grounds. The very adaptability that enables seals to endure harsh conditions becomes a liability in a rapidly changing world, as hunger drives them into predator zones where survival is uncertain. Their decline would not merely signify the loss of a charismatic marine mammal, but would represent a profound disruption of ecological processes that link ocean, land, and atmosphere. This fragility introduces new tension into the ecological narrative, as the disappearance or decline of seal populations could destabilize marine food webs and diminish the resilience of ecosystems that support human livelihoods. Without the regulating influence of seals, prey populations may expand or collapse unpredictably, altering the structure of marine communities and affecting the productivity of fisheries upon which millions depend. Conversely, the reduction of seals as prey would impact apex predators, forcing them to seek alternative food sources and reshaping the dynamics of ocean ecosystems. In this intricate web of interdependence, the survival of seals becomes inseparable from the stability of the marine environments that sustain life across the planet. As hunger continues to drive seals into high-risk feeding grounds, their existence embodies the tension between necessity and danger, revealing the delicate balance upon which survival depends. Each dive into predator-rich waters represents a calculated gamble, a silent negotiation between the need to feed and the threat of becoming prey. Their journeys unfold across shifting seascapes shaped by climate, currents, and ecological change, illustrating how hunger compels life to confront risk in the pursuit of survival. In this enduring struggle, seals become both architects and witnesses of the ocean's evolving equilibrium, their movements shaping the fate of ecosystems that extend from polar ice to temperate coasts. The final image emerges along a desolate expanse of drifting sea ice beneath a pale, luminous sky. A lone seal slips silently into the dark water, its sleek form vanishing beneath the surface as distant shadows circle in the depths below. Hunger drives it forward into waters known to harbor predators, where each moment beneath the waves carries the weight of survival. Above, the frozen horizon stretches endlessly, and the colony waits in silent anticipation of its return. Beneath the surface, currents swirl, prey scatter, and unseen hunters glide through the gloom. In this fragile balance between starvation and predation, the anomaly reveals its truth with unyielding clarity. The ocean does not simply exist. It acts. It reshapes the world. In coral reef ecosystems that support nearly a quarter of all marine biodiversity, the presence of a single predator has altered the balance of life, reshaped fisheries, and influenced the survival of coastal communities across the globe. The grouper, an apex ambush hunter concealed within reef crevices and shadowed overhangs, exerts a powerful regulatory force over fish populations that maintain the health of coral reefs and the productivity of tropical seas. By controlling herbivorous and carnivorous prey alike, groupers indirectly shape algal growth, coral recruitment, and the structural integrity of reef systems that protect coastlines from erosion and storm surges. Yet beneath this ecological influence lies a fragile tension. When prey becomes scarce, hunger compels the grouper to abandon patience and strike more frequently, transforming its calculated ambush strategy into a costly cycle of repeated effort and diminishing returns. In this silent escalation, the behavior of a single predator reverberates across ecosystems and economies, revealing how necessity can reshape the dynamics of the ocean on a planetary scale. The biological machinery that defines the grouper's hunting strategy represents one of evolution's most refined ambush mechanisms. Possessing a robust, laterally compressed body and an enormous cavernous mouth, the grouper is engineered for explosive suction feeding. When prey approaches within range, powerful cranial muscles expand the buccal cavity in a fraction of a second, generating a vacuum that draws water and prey inward with extraordinary force. This rapid expansion is accompanied by protrusion of the jaws and flaring of the gill covers, creating a pressure gradient that overwhelms even agile fish before they can react. The grouper's muscular body remains motionless until the precise moment of attack, conserving energy while relying on camouflage and environmental awareness. Mottled skin patterns mimic the textures of coral and rock, allowing the predator to blend seamlessly into its surroundings, while highly sensitive lateral line systems detect subtle vibrations that betray the presence of unsuspecting prey. This suite of anatomical and physiological adaptations enables the grouper to dominate reef environments through efficiency rather than speed, striking only when success is almost certain. Under stable ecological conditions, this ambush strategy minimizes energy expenditure and maximizes hunting efficiency. The grouper may remain motionless for extended periods, conserving metabolic reserves while waiting for prey to wander within striking distance. However, environmental fluctuations, overfishing, and habitat degradation disrupt the availability of prey species, forcing groupers to alter their behavior in response to scarcity. Hunger drives them to increase the frequency of their attacks, abandoning patience in favor of urgency. Each additional strike demands rapid muscular contraction and precise coordination, consuming valuable energy reserves and reducing overall hunting efficiency. As failed attempts accumulate, the predator's strength diminishes, transforming its once precise ambush into a desperate cycle of exertion and depletion. The very strategy that once ensured survival becomes a liability when prey becomes scarce, illustrating the delicate balance between efficiency and endurance in reef ecosystems. This behavioral shift triggers cascading effects throughout the coral reef community. As groupers increase their hunting frequency, they exert intensified predation pressure on smaller fish populations, altering the distribution and behavior of prey species across the reef. Herbivorous fish, which play a crucial role in controlling algal growth, may decline in areas where groupers hunt more aggressively, allowing algae to overgrow and smother coral colonies. The resulting imbalance reduces coral recruitment and weakens the structural complexity of the reef, diminishing its capacity to support biodiversity and protect coastlines from wave action. Each failed ambush and repeated strike thus becomes an ecological event, influencing the resilience of coral ecosystems that serve as nurseries for countless marine species and as natural barriers safeguarding human communities. A surprising escalation emerges from the role groupers play in maintaining the delicate equilibrium between coral and algae, a balance essential to the stability of tropical marine ecosystems. By regulating populations of mid-level predators and herbivores, groupers indirectly influence nutrient cycling and energy flow within reef systems. When hunger compels them to hunt more frequently, their altered predation patterns can disrupt this equilibrium, leading to shifts in species composition that ripple through the ecosystem. In regions where groupers decline due to overfishing or environmental stress, the absence of their regulatory influence may allow prey populations to proliferate unchecked, destabilizing food webs and accelerating the degradation of coral reefs. The increased frequency of ambush attempts, driven by hunger, thus reverberates through ecological networks, shaping the fate of ecosystems upon which millions of species depend. The cascade extends beyond the reef into coastal environments and global climate systems. Healthy coral reefs contribute to carbon sequestration and support seagrass meadows and mangrove forests that store vast quantities of carbon and protect shorelines from erosion. By influencing the balance of reef communities, groupers indirectly affect the productivity and resilience of these interconnected habitats. When repeated failed hunts weaken grouper populations, The resulting ecological imbalance can undermine the stability of reef systems, reducing their capacity to buffer coastlines against storms and rising sea levels. In this way, the energetic struggles of a single predator become intertwined with the broader dynamics of climate regulation and coastal protection, illustrating the far-reaching consequences of behavioral adaptation in marine ecosystems. Human civilization has long been linked to the fate of groupers, whose ecological and economic significance extends across tropical regions worldwide. As highly valued food fish, groupers support commercial and artisanal fisheries that sustain livelihoods and provide essential sources of protein for coastal communities. Their presence within reef ecosystems reflects the health and productivity of marine environments that underpin tourism, fisheries, and cultural traditions. When hunger forces groupers to increase their hunting frequency, weakened individuals may experience reduced reproductive success, leading to population declines that impact fisheries and global seafood markets. The delicate balance between predator and prey thus intersects with human economies, demonstrating how the survival strategies of marine predators influence food security and economic stability on a global scale. Scientific research into grouper behavior has further illuminated the complexity of reef ecosystems and informed conservation strategies aimed at preserving marine biodiversity. Studies of their ambush mechanics have revealed insights into biomechanics and hydrodynamics, inspiring technological innovations in engineering and robotics. Investigations into their reproductive biology, including synchronized spawning aggregations, have advanced understanding of population dynamics and ecosystem resilience. These discoveries highlight the intricate relationship between biological adaptation and human knowledge, illustrating how the study of a single predator can illuminate broader ecological processes and inform efforts to sustain the health of the world's oceans. An unexpected twist reframes the narrative of strength and dominance associated with the grouper. Despite their formidable size and ecological influence, groupers are acutely vulnerable to environmental disruption and overexploitation. Many species form predictable spawning aggregations, gathering in large numbers at specific times and locations, a strategy that maximizes reproductive success but also renders them highly susceptible to overfishing. When populations decline, the loss of mature individuals disrupts reproductive cycles and weakens the resilience of reef ecosystems. Hunger-driven increases in ambush frequency, coupled with declining prey availability, further exacerbate energetic stress, leaving weakened groupers less capable of sustaining themselves and reproducing successfully. The very behaviors that define their ecological role become liabilities in a rapidly changing ocean. This fragility introduces new tension into the ecological narrative, as the decline of grouper populations could destabilize reef ecosystems and diminish the resilience of coastal environments. Without the regulatory influence of these apex predators, prey populations may expand or collapse unpredictably, altering the composition of reef communities and accelerating coral degradation. The loss of groupers would not merely signify the disappearance of a single species, but would represent a disruption of ecological processes that link biodiversity, coastal protection, and human survival. Their weakening, driven by repeated failed hunts and environmental pressures, underscores the delicate balance upon which marine ecosystems depend. As hunger continues to drive groupers to strike with increasing frequency, their existence embodies the tension between efficiency and survival. Each ambush represents a calculated risk, a precise burst of power that draws upon dwindling reserves of energy. In times of abundance, patience ensures success, but scarcity transforms strategy into desperation, compelling the predator to abandon restraint in pursuit of sustenance. Repeated failure erodes strength, reducing the predator's capacity to hunt and reproduce, while the reef around it responds to the shifting rhythms of predation and scarcity. In this silent contest between hunger and endurance, the grouper becomes both a guardian and a casualty of the ecosystem it helps to sustain. The closing image unfolds beneath a sunlit reef where shafts of turquoise light penetrate the water, illuminating a labyrinth of coral and shadow. A solitary grouper hovers motionless within a rocky crevice, its mottled skin blending seamlessly with the surrounding reef. Prey fish dart cautiously through the water column, aware of the predator's presence, yet driven by their own need to feed. Hunger tightens its grip, and with sudden force, the grouper lunges forward in another ambush, the water surging inward as jaws expand in a burst of suction. The strike fails, and the predator retreats once more into the shadows, its strength diminished, but its instinct unbroken. Around it, the reef pulses with life. Currents carry nutrients across the ocean, and the balance of the ecosystem shifts with each silent attempt. In this fragile equilibrium of patience and necessity, the anomaly reveals its truth with unmistakable clarity. The ocean does not simply exist. It acts. It reshapes the world. Entire coastlines have been transformed by a creature no larger than a clenched fist, a silent engineer capable of altering marine landscapes, destabilizing fisheries, and reshaping global carbon dynamics. Sea urchins, armored in spines and driven by insatiable hunger, have converted vibrant kelp forests and thriving coral ecosystems into desolate underwater barrens, stripping life from habitats that sustain biodiversity and protect shorelines. These small herbivores, when unchecked by predators or driven by shifts in food availability, unleash ecological cascades that ripple across oceans and economies alike. Their grazing has redefined entire marine provinces, influencing coastal productivity, altering climate-regulating ecosystems, and disrupting food webs that support human civilization. In this paradox of scale, a slow-moving echinoderm becomes an agent of planetary change, demonstrating how hunger does not merely threaten survival, but possesses the power to reshape the world itself. The biological mechanism behind this transformation reveals a finely tuned evolutionary design adapted for relentless grazing. Sea urchins possess a rigid calcareous skeleton known as a test, covered in movable spines that provide protection from predators and assist in locomotion across rocky substrates and coral frameworks. Beneath this armored exterior lies a sophisticated feeding apparatus known as Aristotle's lantern, a complex arrangement of interlocking calcified plates and muscles that operate as a 5-part jaw. This structure allows the urchin to scrape, bite, and grind algae from surfaces with remarkable efficiency, eroding both rock and coral in the process. Tube feet, powered by a hydraulic water vascular system, enable precise movement and adhesion, allowing the urchin to navigate turbulent environments while maintaining a steady grip on feeding grounds. These adaptations, refined over hundreds of millions of years, render sea urchins exceptionally effective grazers, capable of consuming vast quantities of algae and exerting profound influence over the structure of marine ecosystems. Under balanced ecological conditions, sea urchins play a stabilizing role within coastal habitats, maintaining equilibrium between algal growth and coral or kelp development. By grazing on fast-growing algae, they prevent overgrowth that could otherwise smother corals or overshadow kelp forests, preserving the structural complexity of these ecosystems. However, when predator populations decline or environmental disturbances alter food availability, this balance collapses. In the absence of natural controls such as sea otters, large fish and lobsters, sea urchin populations expand rapidly, their collective appetite intensifying into a force of ecological transformation. Hunger drives them to graze continuously, stripping surfaces bare and eroding the foundations of habitats that once supported diverse marine life. What begins as individual feeding behavior escalates into a systemic shift, converting lush underwater forests into barren seascapes devoid of shelter and biodiversity. This transformation initiates cascading effects throughout marine food webs, reverberating across coastal ecosystems and beyond. As kelp forests disappear under relentless grazing, the intricate habitats they provide for fish, crustaceans, and marine mammals vanish, leading to declines in species abundance and diversity. The loss of kelp disrupts nutrient cycling, reduces primary productivity, and diminishes the capacity of coastal ecosystems to absorb carbon dioxide from the atmosphere. Without the stabilizing influence of kelp, wave energy reaches shorelines with greater intensity, accelerating coastal erosion and increasing vulnerability to storms. The expansion of sea urchin barrens thus represents more than a localized ecological shift. It becomes a driver of environmental change that influences climate regulation, coastal protection, and the resilience of marine ecosystems on a global scale. A surprising escalation emerges from the interaction between sea urchins and coral reefs, where their grazing can alter the delicate balance between algae and coral growth. In regions where herbivorous fish decline due to overfishing or environmental stress, sea urchins may temporarily assume a critical role in maintaining reef health by controlling algal proliferation. Yet when their populations surge unchecked, excessive grazing erodes coral substrates and inhibits reef recovery, undermining the structural integrity of ecosystems that support fisheries and protect coastal communities. This duality underscores the anomaly of the sea urchin, an organism capable of both sustaining and destabilizing marine environments depending on ecological context. Hunger, amplified by the absence of predators or shifts in food patterns, transforms a beneficial grazer into an agent of ecological upheaval. The cascade extends into global climate systems where the loss of kelp forests and seagrass meadows diminishes the ocean's capacity to sequester carbon. These vegetated habitats, often referred to as blue carbon ecosystems, store significant amounts of carbon in their biomass and sediments, mitigating the effects of climate change. When sea urchins overgraze these environments, carbon sequestration declines, and stored carbon may be released back into the atmosphere, contributing to global warming. The conversion of productive habitats into barren landscapes thus represents a feedback loop linking ecological imbalance to climate regulation. In this context, the feeding behavior of sea urchins influences not only the structure of marine ecosystems, but also the stability of Earth's climate, illustrating how localized biological processes can reverberate across planetary systems. Human civilization has long been intertwined with the ecological influence of sea urchins, whose presence affects fisheries, economies, and coastal livelihoods. The collapse of kelp forests due to urchin overgrazing has led to declines in commercially valuable species, such as abalone, rockfish, and lobster, disrupting fisheries that sustain coastal communities worldwide. Conversely, in regions where sea urchin populations flourish, they have become valuable commodities themselves, harvested for their roe in global seafood markets. This economic paradox highlights the intricate relationship between human enterprise and marine ecosystems, where the abundance of a single species can simultaneously threaten biodiversity and sustain livelihoods. Efforts to manage urchin populations, including the restoration of predator species and the development of sustainable harvesting practices, reflect the growing recognition of their ecological and economic significance. Scientific research into sea urchin biology has further illuminated their role in ecosystem dynamics and contributed to advancements in developmental biology, genetics, and environmental science. Their embryos have served as model organisms for studying cellular processes, offering insights into fertilization, gene expression, and evolutionary biology. These discoveries underscore the broader impact of sea urchins beyond their ecological influence, demonstrating how the study of a single species can advance human understanding of life itself. Yet their ecological dominance, driven by hunger and unchecked population growth, serves as a reminder of the delicate balance that governs marine ecosystems and the far-reaching consequences of disruption. An unexpected twist reframes the narrative of resilience and ecological power associated with sea urchins. Despite their formidable capacity to transform marine landscapes, they are acutely vulnerable to environmental change and disease. Marine heat waves, ocean acidification, and pathogenic outbreaks have decimated urchin populations in certain regions, leading to rapid recoveries of kelp forests and the resurgence of biodiversity. This fragility reveals the precarious equilibrium upon which their ecological influence depends, as fluctuations in environmental conditions can shift them from dominant grazers to declining populations within remarkably short timeframes. The very organisms capable of reshaping entire ecosystems are themselves susceptible to the forces of a changing ocean. This vulnerability introduces new tension into the ecological narrative, as the decline or proliferation of sea urchin populations can destabilize marine environments in unpredictable ways. When predator populations are absent or environmental conditions favor urchin expansion, overgrazing transforms vibrant ecosystems into barren landscapes, reducing biodiversity and diminishing the resilience of coastal habitats. Conversely, sudden declines in urchin populations may trigger rapid ecological shifts that reshape food webs and alter nutrient cycles. The balance between these extremes underscores the interconnectedness of marine ecosystems, where the hunger of a single species can dictate the fate of entire habitats and influence the stability of environmental systems upon which human societies depend. As hunger continues to drive sea urchins to graze relentlessly across the ocean floor, their existence embodies the tension between survival and transformation. Each bite of algae contributes to a process that extends far beyond individual sustenance, reshaping habitats, redistributing nutrients, and altering the balance of life within the sea. Their movements, slow and deliberate, conceal a force of ecological engineering that operates across vast spatial and temporal scales. In the absence of predators or shifts in food patterns, their collective appetite becomes an unstoppable force, converting thriving ecosystems into barren seascapes and redefining the boundaries of marine life. The closing image unfolds along a rocky coastline where sunlight filters through crystalline water, illuminating a once lush kelp forest now reduced to a silent expanse of stone. Sea urchins cling to the barren substrate, their spines casting delicate shadows across the sea floor as currents carry fragments of drifting algae through the empty water column. In the distance, waves crash against the shore, and the absence of swaying kelp exposes the coastline to the relentless force of the sea. Beneath the surface, life struggles to reclaim its foothold, while the quiet persistence of the urchins continues to sculpt the underwater landscape. In this enduring cycle of growth and destruction, the anomaly reveals its truth with unmistakable clarity. The ocean does not simply exist. It acts. It reshapes the world.